Hello there, and welcome to Science for Sleep, where curiosity takes the long way home and science unfolds at a pace gentle enough to dream by. Tonight, we'll drift together through a universe that never truly stands still. If you listen closely, you might almost hear it, the slow and endless turning of everything. From the swirl of galaxies across the dark to the spin of tiny particles smaller than dust, the cosmos is in motion everywhere, all at once, and somehow, amid that constant movement, we've built a life that feels still enough to rest in, or at least we try to. So before we begin, take a breath, let it rise and fall, like the turning of a planet beneath the sun. If you find this quiet journey soothing, I'd be ever so grateful if you gave the video a like, or maybe subscribed, so this little corner of calm can find others who might need it too. Now, wherever you are, whatever time it happens to be in your corner of the world, let's drift gently into the mystery of motion. Because while we often think of the universe as vast, cold and still, the truth is it never stops spinning. Not for a moment, not anywhere. The room you're in right now, the air around you, the ground beneath you, the planet itself, is moving through space at unimaginable speed. You can't feel it, because everything around you moves with it. The walls, the sky, your own heartbeat, all part of a vast coordinated motion that began long before there was even an Earth to stand on. The floor feels steady only because the scale of our senses isn't built to notice cosmic motion. Yet if you could step back far enough to see the whole planet at once, you'd see it turning endlessly, one half facing the light, one half resting in shadow, a marble spinning slowly in the dark. Every sunrise, every tide, every breeze is shaped by that spin. The Earth's rotation gives rhythm to our days, sets the boundaries of sleep and waking, guides the winds and stirs the oceans. Without it, the planet would be locked in an eternal stillness, half frozen, half scorched. The turning saves us from that fate. It makes life possible, balancing light and dark, warm and cold, work and rest. When you fall asleep, you're really just trusting the spin, letting it carry you gently through the night toward another dawn. But the spin doesn't stop with the Earth. The moon turns too, though more quietly, keeping one face toward us as it circles the planet. The sun spins as well, its surface boiling and churning like a restless sea. Even the planets beyond, each of them rotates, tipped, tilted, or tumbling in their own peculiar ways. Saturn whirls at breathtaking speed. Venus drifts in a slow reverse. Jupiter, so vast that it could swallow more than 1,000 Earths, spins so fast that its days last less than 10 hours. It's as though every world in the solar system has its own tempo, a private rhythm in the grand cosmic dance. And the solar system itself is spinning too. The planets orbit around the sun orbits the centre of the Milky Way, and the Milky Way turns slowly within a cluster of galaxies, which in turn rotate within the greater web of the universe. Every atom in your body, every speck of dust underfoot is caught up in that same endless rotation. Motion is not the exception, it's the rule. We often talk about stillness as if it's something real, something we can hold on to. But stillness is an illusion. It's a relative pause in the middle of motion too vast to see. Even when you sit completely still, hands folded, eyes closed, every atom inside you is moving. Electrons spin, molecules vibrate, cells divide, blood flows. Your very thoughts are pulses of energy racing through networks of neurons. You are not still, you're made of motion. It's strange to think about, but comforting too. The same laws that spin galaxies also spin you. The same invisible forces that set planets in motion keep your heart beating and your breath steady. The symmetry of it, the shared pattern, suggests that movement isn't just something that happens in the universe, it's what the universe is. And the deeper we look, the more it becomes clear that rotation is one of its most fundamental expressions. Scientists have a name for this kind of motion, They call it angular momentum. It's the measure of how much an object is spinning, and once something begins to spin, it's remarkably stubborn about stopping. Angular momentum is conserved, which means unless some outside force interferes, a spinning object will keep on turning forever. That's why planets continue rotating billions of years after they formed. There's nothing in the vacuum of space to slow them down. They spin because they always have, and because nothing tells them not to. You can feel a hint of this principle every time you ride a bicycle or a spinning chair. If you start to rotate and pull your arms in, you spin faster. Push them out, and you slow down. It's the same law that keeps figure skaters graceful and satellites stable. The universe follows that rule too, only on scales so vast we can barely comprehend them. Somewhere in the deep past, the first great clouds of gas began to collapse under their own gravity. As they fell inward, they started to spin faster and faster, just like a skater pulling in their arms. That spin never stopped. It became stars, planets, moons, everything we now see. Imagine that for a moment. The spin you feel in a planet's day, the rotation that turns the night sky, traces back to the first moments of the universe. Before stars, before galaxies, before time as we measure it, there was already motion. Tiny fluctuations in the newborn cosmos, ripples of density and energy, began to twist, to swirl, to rotate. That spin carried forward, preserved by the laws of physics, spreading into every structure that would ever form. The universe was born moving, and it never stopped. Even galaxies, vast collections of stars and dust and gas, owe their rotation to those early twists. As matter gathered under gravity, it didn't fall straight inward. It curved, spiraled, found paths of least resistance that turned collapse into rotation. The Milky Way's slow spin, which takes more than 200 million years to complete a single revolution, began with those first subtle motions. If you could watch it from afar, you'd see a disk of hundreds of billions of stars orbiting a dark, invisible center, each one tracing a perfect curve through space. From a distance it looks peaceful, almost static, but in truth it's a whirlpool of unimaginable scale. That motion is what gives galaxies their shape. Without rotation, the Milky Way would be a loose, shapeless cloud. Spin flattens it, organizes it, creates the spiral arms where new stars are born. Even chaos, it seems, takes on grace when it starts to spin. And inside those galaxies the same rule repeats. Stars form from spinning clouds of gas. Planets form from the swirling disks around those stars. Moons form from debris left spinning around planets. It's a cascade of rotation, one layer feeding the next, an infinite nesting of motion within motion. When scientists look for new worlds beyond our solar system, they often detect them by the slight wobble they cause in their parent stars. A tiny rhythmic movement, a trace of that eternal spin. It's humbling to think that even the methods we use to explore the universe depend on noticing how it turns. Motion isn't just a feature of existence, it's the signature of it. But this raises a question that's lingered since the first humans looked at the stars and wondered why they moved. Why spinning? Why not stillness? Why should the universe prefer to twist rather than rest? The answer lies in the nature of symmetry itself. Perfect stillness would require perfect balance, and perfect balance is rare in nature. The slightest irregularity, an uneven density, a bit of turbulence, becomes amplified as gravity pulls matter together. The result is rotation. Spin is the universe's way of distributing imbalance, of turning asymmetry into stability. If a cloud of gas were to collapse completely motionless, every particle falling straight inward, it would create an impossible singularity. But if the cloud has even a whisper of rotation, that motion resists collapse, spreading the forces out. It becomes stable. Spin, in other words, is how the universe holds itself together. Without it, stars might never have formed, planets might never have coalesced. There might be no Earth, no oceans, no you listening here tonight. Even in the tiniest scales, the same principle holds. In the quantum world, particles possess a kind of intrinsic spin, a built-in angular momentum that isn't caused by physical rotation but behaves as if it were. Electrons, protons, neutrons all have spin values that determine how they interact, how atoms form, how light behaves. Spin, at this level, is not something that happens to matter. It's part of what matter is. The entire universe, from its largest galaxies to its smallest particles, is unified by this rhythm of rotation. And though we can describe it with equations and measurements, it still feels somehow magical. To realize that motion is not a condition but a foundation, that everything is turning not because something made it spin but because spinning is the natural state of being, changes how we see our place in the cosmos. The ground beneath you, the stars above you, even the atoms in your skin are all participants in the same vast and ancient turning. The more you think about it, the more it becomes clear that there's no true edge to this motion. Every spinning thing belongs to something larger that's spinning too. The Earth rotates around its axis, revolves around the Sun, which moves through the Milky Way, which orbits a cluster center, which drifts through expanding space, and at every level angular momentum carries forward, unbroken, persistent. The universe doesn't waste motion, it transforms it, passes it on, folds it into new structures. The spin never disappears. Perhaps that's why humans are so fascinated by circles, wheels, orbits, cycles, all reflections of the same pattern we see everywhere in nature. The planets, the seasons, the heartbeat, the breath, all rotations in one form or another. Maybe we recognize somewhere deep inside that we're built from a universe that loves to turn. Even when we rest, the world keeps moving. The night sky changes position. The stars rise and set. The galaxy spins imperceptibly. Yet the motion is not something to resist. It's something to belong to. Every spin, every orbit, every cycle is another expression of continuity, of persistence, of life carrying forward through change. So as you listen, as the world outside grows quieter, remember that the stillness you feel isn't truly still. It's a momentary pause within an unending movement. You're floating on a rotating world, orbiting a spinning star, moving through a galaxy that's turning within an expanding cosmos. Motion isn't the opposite of rest. It's the condition that makes rest possible. And somewhere out there, far beyond the edge of what we can see, the universe continues to turn, silently, endlessly, beautifully. The world feels still because our senses are too small to notice the vastness of its motion. Yet the more we look, the more obvious it becomes that nothing, absolutely nothing, stands still. Motion is not an occasional event in the universe. It is the baseline, the foundation, the silent hum beneath all existence. Even the concept of rest, so central to how we live and speak, is a local illusion, a pause only from our point of view, not from the cosmos itself. Right now, as you sit or lie wherever you are, the ground under you is spinning at more than 1,000 miles per hour around the Earth's axis. At the same time, the Earth is orbiting the Sun at about 67,000 miles per hour. The entire solar system is hurtling around the centre of the Milky Way at nearly 500,000 miles per hour, and the Milky Way itself is gliding through the universe at more than 1,000,000 miles per hour relative to the background of cosmic radiation left over from the Big Bang. The numbers don't even feel real. They're too large to grasp, too constant to feel, yet they're happening every moment. What makes all of this motion even more remarkable is how stable it is. The planets don't drift aimlessly. They follow graceful paths that repeat with astonishing precision. The solar system is a choreography of balance, gravity holding everything together, motion keeping it all apart. If any of those movements stopped, the balance would collapse. The Earth would fall into the Sun, the Moon would crash into Earth, and the planets would scatter into the void. Spinning is not chaos, it's what prevents chaos. Scientists sometimes describe the universe as a dynamic equilibrium. Everything is in motion, yet the overall structure remains stable because the forces involved balance one another perfectly. The inward pull of gravity, the outward momentum of motion, the subtle exchanges of energy, they all conspire to create harmony. When we talk about spinning, we're not just describing movement, we're describing the universe's way of maintaining order. Think of a spinning top. When it's still, it wobbles and falls, but when it's spinning, it stands upright, stable, almost serene. The same principle plays out on the grandest scale imaginable. A planet spins because it helps it stay balanced as it travels through space. A galaxy spins because rotation distributes its mass evenly, keeping it from collapsing inward. Spin is stability in motion. The very thing that seems restless is, paradoxically, what keeps everything in place. But where does all this motion come from? It's not as if the universe had an external push to start it moving. There's nothing outside it to turn the key. The answer lies in how the universe began, not in a perfect symmetry, but in tiny imperfections. When the Big Bang occurred, the universe didn't expand as a perfectly even sphere. It was filled with minute fluctuations in density and energy. These irregularities became the seeds of structure. Gravity amplified them, drawing matter together into clumps. But gravity doesn't pull in perfectly straight lines. When matter falls inward unevenly, it starts to twist. Those tiny asymmetries turn into spin. It's easy to picture it as a kind of cosmic inheritance. The early universe didn't hand out rotation deliberately, it simply couldn't avoid it. The laws of physics make spin almost inevitable whenever matter interacts. Once an object gains angular momentum, it keeps it. There's no cosmic friction to slow it down. In space, motion is forever. The beauty of this is how universal it is. Whether you're looking at a swirling storm on Jupiter, a hurricane on Earth, or a spiral galaxy 500 million light-years away, the same physical principles are at work. The scale changes, but the story doesn't. Rotation emerges wherever matter moves and gathers. It's not something special or rare. It's the normal state of nature. Even within your own body, the same dynamic plays out. The atoms that make up your cells have electrons with intrinsic spin. The fluids in your veins move in spirals. Air flows through your lungs in gentle vortices as you breathe. You are part of this spinning universe in every measurable way. The forces that turn stars and galaxies also shape you, not metaphorically, but literally. If you could see motion without boundaries, see not just the turning of the Earth, but the orbits and rotations nested within it. You'd realize that the entire universe resembles one vast interlocking system of rotations. Each layer contributes to the next. The rotation of the Earth helps maintain its magnetic field. That field protects the atmosphere, allowing life to exist. Life, in turn, adapts to the planet's cycles of day and night, seasons and tides. Motion creates the conditions for existence, and existence adapts back to the motion. Even chaos carries order in this system. The storms that rage across Jupiter's surface, the swirling gases around newborn stars, the immense accretion disks spiraling into black holes, they all follow the same physics that governs a spinning coin or a child's toy. What changes is the scale, the temperature, the density. The laws themselves are consistent. The elegance of that simplicity is what makes the universe intelligible. Our own galaxy, the Milky Way, rotates once every 230 million years. That means the solar system has only made about 20 journeys around the galactic centre since it formed. Everything we know, all of human history, all of evolution, has taken place in a single sweep of the galaxy's rotation, and the galaxy isn't turning in isolation. It's part of a cluster of galaxies, each one moving, twisting, colliding, merging, reshaping. Even the empty space between them is stretching as the universe expands. When we talk about expansion, it's easy to imagine it as a calm swelling, like a balloon. But in reality, expansion and spin are intertwined. As space stretches, it carries momentum with it. The cosmic web, those vast filaments of galaxies that stretch across the universe, isn't static. It's twisting, shearing, flowing. Rotation occurs even on the scale of the entire cosmos. There's a curious balance here. On the one hand, the universe expands, pushing everything apart. On the other, gravity draws matter together, forming rotating structures. These two forces, expansion and attraction, shape the universe's texture. Without expansion, everything would collapse into a single dense mass. Without rotation, everything would fall straight inward. Together, they produce a cosmos that moves, breathes, evolves. This pattern of motion repeats endlessly. On Earth, hurricanes spin because of the planet's rotation, the Coriolis effect turning air currents into spirals. In stars, plasma rotates, generating magnetic fields. In galaxies, dark matter halos spin, guiding the rotation of luminous matter. Motion begets motion. Once started, it cascades through every level of structure. There's something deeply satisfying about that. The idea that all things, from dust to planets to galaxies, are united by motion gives a sense of coherence to an otherwise chaotic universe. It means there's a kind of continuity between the smallest and the largest scales, a bridge from the quantum to the cosmic. You could think of it as a hierarchy of spins, each one passing its momentum to the next, like gears in an infinite clockwork. And yet, for all that order, the universe's motion is far from predictable in detail. Rotation creates turbulence, and turbulence breeds complexity. The shapes of clouds, the paths of stars, the swirls of galaxies, all are results of countless interacting spins. What looks serene from a distance is, up close, a riot of eddies and currents. It's this tension between order and chaos that makes the universe both stable and alive. Over billions of years, these rotations have shaped everything we see. The planets formed from spinning disks of gas and dust left over after their stars were born. Those disks flattened as they rotated, the particles colliding and sticking together, forming clumps that grew into worlds. The leftover debris formed moons and asteroids, all sharing the same general direction of spin. The pattern is consistent across almost every planetary system observed. Spin is written into the DNA of creation. It doesn't end there. Stars themselves spin. When a massive star runs out of fuel and collapses, its core compresses into a neutron star, a city-sized remnant spinning hundreds of times per second. These are called pulsars. They emit beams of radiation that sweep across space like cosmic lighthouses. Their rotation is so stable that scientists use them as natural clocks, measuring time with more precision than most human-made devices. Even in death, stars keep turning, their angular momentum preserved in compact, unstoppable motion. And at the other extreme, black holes represent the universe's most extreme expression of spin. When a massive star collapses into a black hole, all its rotation becomes concentrated. The result is an object so dense that it drags space itself into motion around it. Near a spinning black hole, space and time are twisted together, forming a region where nothing can stand still. The spin becomes space itself. So from the smallest particles to the largest cosmic structures, spin is everywhere. It defines the way matter behaves, the way energy flows, the way gravity shapes space. It even influences how we perceive time. A day, after all, is nothing more than a measure of how long it takes the Earth to rotate once. The rising and setting of the sun, the rhythm of life on this planet, all trace back to a simple act of motion. It's tempting to think of the universe's movement as separate from us, something happening out there while we stay here. But the truth is, the two are inseparable. You're spinning with the Earth, orbiting the sun, circling the galactic center, drifting with the cosmic flow. Every second of your existence is embedded in motion. Stillness, the thing we crave at the end of the day, is really just alignment with these larger patterns. When you lie down and close your eyes, the Earth keeps turning. The stars wheel slowly overhead. The galaxy spins, the universe expands. You're part of all of it, carried gently through space by forces so vast you can't feel them. That might sound immense, but it's strangely comforting. Because motion, once you realize it's everywhere, stops feeling like something that threatens peace. It becomes the very fabric of peace itself. The universe in motion is not a restless place. It's an organized, balanced, endlessly unfolding system. The spinning of galaxies is not chaos, it's the natural expression of the laws that govern everything. What we call rest, what we call quiet, is simply the small corner of that motion we happen to be synchronized with. Every atom, every star, every galaxy carries its share of angular momentum from the beginning of time. That momentum doesn't vanish. It transforms, divides, merges, but it never disappears. The spin of the universe is its memory, the echo of its birth still resonating in every turn of every world. For most of human history, people imagine the world as still. The stars were thought to be fixed in crystal spheres, turning in perfect circles above an unmoving earth. The ground beneath our feet felt solid, unshifting, eternal. Even now, with everything we've learned about rotation, it's easy to understand why that belief lingered for so long. Stillness is comforting. It feels safe. But the more we look, the clearer it becomes that stillness as we experience it is not the absence of motion but a brief pause within it. The kind of stillness we crave isn't real in any physical sense. It's a momentary illusion the mind creates so we can rest inside a universe that never stops moving. The need for stillness comes from the same mind that perceives motion. Our senses evolved to notice change, to detect movement, sound, temperature, light. Without contrast, perception fades. The constant spin of the Earth, the orbit of the planets, even the gentle pull of gravity are too steady to feel. Our bodies filter them out so we can focus on what matters for survival. Sudden shifts, new sounds, flashes of colour. That's why the cosmic motion all around us feels silent. We are tuned to the small fluctuations within it, not the grand rotation itself. Yet every experience of stillness is built on motion. When you lie still, your heart keeps beating. Blood flows through countless vessels. Electrical impulses cross your brain. Even as you breathe quietly, air moves in and out, swirling through microscopic pathways. Inside each cell, molecules vibrate, proteins twist. DNA unwinds and rewinds in endless repetition. To be alive is to move. The body never stops, even when the mind calls it rest. What we call stillness, then, is really synchronization. A moment when motion aligns so perfectly with our perception that it feels like a pause. The Earth keeps turning, but we move with it. The room keeps shifting through space, but so do we. The sense of stillness arises not from the absence of motion, but from harmony with it. We stop noticing because everything, including us, is moving together. In that sense, stillness is relative. A leaf drifting on a stream may look motionless to someone floating beside it, yet to someone standing on the bank, both are gliding swiftly past. Astronauts orbiting Earth feel weightless, suspended in calm, but they're falling perpetually around the planet at thousands of miles per hour. Stillness depends on the frame of reference. It is always local, always temporary, always defined by something moving more or less than we are. Even our thoughts behave this way. A quiet mind feels still because the flow of thoughts slows enough to match our awareness. But beneath that stillness, neurons continue to fire, chemical messengers continue to drift, signals continue to pass. The sense of calm is not a halt in activity. It's a lowering of noise, a temporary balance between impulses. When that happens, the spinning world feels far away, though it never truly is. Humans have long sought this balance between movement and rest. Meditation, ritual, music, breathing. These are ways to align internal rhythms with external ones. The heart slows, the breath deepens, the sense of time stretches. It's not that the universe quiets, it's that we learn to match its tempo. Even the monks who first built clocks to mark their prayers did so not to escape time's motion, but to move in rhythm with it. The gong or bell that punctuated their day was not a command, but a reminder that every moment has its place in the larger cycle. There's a kind of irony in the fact that the technologies we've created to measure stillness, cameras, gyroscopes, seismographs, only prove how much movement there always is. Point a telescope at a distant galaxy and hold it steady, and you'll still see the faint drift of stars, the flicker of light stretched by motion through space. Even solid rock, when measured carefully enough, trembles. The surface of the planet quivers with microscopic vibrations from wind, waves, footsteps, even the faint echo of the moon's pull. Nothing is truly still, not even mountains. When we imagine stillness, we often picture a scene like a calm lake or a quiet night. But even there, motion persists. Beneath the surface of that lake, water molecules move in intricate patterns. In the sky above, air currents shift and swirl invisibly. The stars that appear fixed are moving across the galaxy at extraordinary speeds. The stillness we see is a perspective, not a condition. It's what happens when motion becomes too smooth, too constant, or too vast to perceive. The human desire for stillness may come from the tension of living in such a restless world. Our minds evolved to navigate change, but we also need rest to recover from it. Sleep itself is a rhythm, a state where the conscious mind steps back while the body continues its intricate cycles of repair. Even in sleep, the heart beats, the lungs expand and contract, the eyes twitch with dreams. The body moves through stages, each with its own purpose. We never truly stop. We simply shift to a quieter form of motion. In physics, even what we call empty space is not still. The vacuum of space teems with fluctuations, virtual particles appearing and vanishing in fractions of a second. The very fabric of the cosmos vibrates with quantum energy. On that scale, motion is fundamental. Stillness doesn't exist because energy can't be zero. There's always something happening, however small. The universe breathes at every level, from galaxies down to particles, and even the space between them hums with activity. When you realize that, the idea of absolute stillness becomes almost alien. There's no place to stand apart from motion, because motion is what makes existence possible. The Earth's rotation generates the magnetic field that shields us from radiation. The Moon's orbit stabilizes the planet's tilt, giving us predictable seasons. The Sun's rotation stirs its surface, creating the solar wind that shapes our atmosphere. Life depends on this movement. Stillness, if it truly existed, would mean the end of change, and therefore the end of life. Stillness, then, is not an escape from motion, but a form of participation in it. The calm we find in quiet moments is a kind of resonance. We fall into step with the steady rhythms that sustain us, the turning of the earth, the beating of our hearts, the oscillation of breath. When these align, time feels slower, and the sense of separation from the world softens. It's not that motion stops, it's that we stop resisting it. In a way, this balance between motion and stillness mirrors the balance between order and chaos that defines the cosmos. Rotation itself is a kind of compromise between the two. A spinning system has structure, it's governed by clear physical laws, but it also contains turbulence and unpredictability. Think of a hurricane, organized at a distance, chaotic up close. The same can be said of galaxies and planetary systems. They maintain coherence precisely because motion allows them to absorb disorder without collapsing. Stillness would make them fragile. Motion gives them resilience. The human mind seems to follow the same rule. When thoughts stagnate, creativity fades. Movement, whether physical or mental, keeps the system alive. Stillness isn't the absence of thought, but the space between them, the quiet intervals that make meaning possible. In music, silence defines rhythm. In speech, pauses shape understanding. The universe, too, seems to use stillness as punctuation between motions, a calm not of emptiness but of readiness. It's fascinating that even at the quantum level, spin never disappears. Electrons, protons, and other fundamental particles have intrinsic angular momentum that defines their very identity. Remove that, and the particles cease to be what they are. Spin is not optional. It's essential. The universe's smallest building blocks are never still, and their motion is what gives rise to the structures we perceive as solid. The desk, the wall, the mountain, all are built from restless particles constantly moving, constantly spinning. Our sense of stillness, then, is a matter of perspective layered over countless hidden motions. It's a delicate illusion that allows consciousness to function without being overwhelmed. Imagine if we could perceive every vibration, every atomic movement, every shift of air. It would be unbearable. The mind simplifies the world into manageable pieces, translating constant motion into moments of calm. In that simplification lies both the beauty and the blindness of human experience. Sometimes late at night, when everything grows quiet, the awareness of motion returns. You might feel the faint hum of life around you, the distant sound of the wind, the rhythm of your breathing, the soft pulse behind your ribs. Those are the reminders that stillness is layered, that the calm you feel is built from the synchronization of countless small movements. It's the universe breathing through you, matching its pace to yours for a little while. So when we speak of a brief pause in stillness, what we really mean is a moment of alignment, a second where perception and motion meet, and the vast spinning machinery of the cosmos feels gentle enough to rest within. The pause isn't the absence of motion. It's the moment we notice its grace. Everything continues turning. The earth, the stars, the particles beneath your skin. But in that pause, we see the pattern clearly enough to call it peace. And just as quickly, the feeling shifts. The mind picks up a sound, the body stirs, and the rhythm moves on. The stillness passes, but the motion remains, continuous and kind. There's comfort in that constancy. The universe doesn't stop, and it doesn't need to. It moves smoothly, endlessly, carrying you along with it. If you were to travel back far enough, past the stars and galaxies, past the first clouds of gas, past even the atoms themselves, you would find a universe so small and so dense that motion as we know it barely made sense. There were no stars, no planets, no direction, not even space in any familiar sense. Everything was packed into an unimaginably hot and uniform state. Yet even there, in that primordial simplicity, the seeds of motion already existed. The story of spin begins there, in the first moments after the birth of everything, when the universe itself was learning how to move. At the instant of the Big Bang, the universe didn't explode outward from a point into empty space. Space itself expanded. Matter and energy filled it evenly, stretching in every direction. It's tempting to picture that moment as perfectly balanced, perfectly symmetrical. But perfect symmetry doesn't last. The smallest irregularities, quantum fluctuations in density and temperature, broke that perfection almost immediately. They were tiny, 1 part in 100,000, but they were enough. Gravity noticed. Those tiny imbalances began to grow. Gravity by its nature gathers. It pulls matter toward matter, turning random motion into organized collapse. But those early fluctuations were not evenly distributed. Some regions had slightly more mass, some slightly less. As matter fell toward the denser regions, it didn't fall straight. The uneven pull caused it to curve, to twist, to form vortices. From that twisting came the first hints of rotation. The universe didn't need an external push to start spinning. It only needed imperfection. Angular momentum, the quantity that measures spin, is one of the universe's most strictly conserved properties. Once something has it, it doesn't go away. It can be shared, transferred, transformed, but never destroyed. The total angular momentum of the cosmos has been constant since those first instants. Every turning planet, every orbiting moon, every spinning particle carries a portion of that ancient motion. When we talk about spin, we're not talking about something added later. We're talking about a memory of creation itself. In the earliest fractions of a second, the universe expanded faster than light in an event called inflation. During that expansion, tiny quantum ripples were stretched across cosmic scales. Those ripples became the blueprint for everything that would form later. Clusters of galaxies, voids, filaments. When gravity began to amplify those patterns, motion followed naturally. Nothing in the universe is perfectly still, and the faintest asymmetry becomes rotation once gravity begins to act on it. The cosmic spin, in a sense, began as a side effect of creation's rough edges. As the universe cooled, matter began to separate from radiation. At first, it was a soup of particles and light, constantly colliding, scattering, and recombining. Over time, as expansion stretched space and temperatures dropped, atoms could finally form. Hydrogen and helium became the building blocks of gas clouds that drifted through the young cosmos. Within those clouds, gravity worked patiently, drawing material together. But gravity doesn't pull evenly on every side. The slightest nudge, an uneven density, a passing wave, the faint push of radiation was enough to give the collapsing cloud a spin. Once the cloud started rotating, conservation of angular momentum took over. As it shrank under gravity, it spun faster, just like a skater pulling in their arms. That acceleration of rotation became one of the universe's most reliable patterns. Every collapsing region, from vast galaxies to individual stars, inherited some amount of spin from its initial conditions. The result was a cosmos built on rotation at every scale. Astronomers have long wondered whether the universe as a whole might have a preferred direction of spin. Some early models suggested that it might rotate as a single entity, like a massive cosmic gyroscope. But so far, observations suggest no overall spin, no grand axis around which everything turns. Instead, local rotations dominate. Galaxies spin in random orientations, half clockwise, half counterclockwise when viewed from Earth. The balance between them is nearly perfect, as though the universe's total angular momentum adds up to zero, even though every part within it is spinning furiously. This balance makes sense. In the beginning, there was no direction to prefer. Motion developed from randomness, and while local regions gained spin, the overall universe stayed neutral. It's as if every rotation is matched somewhere by another in the opposite direction, preserving equilibrium. What we see now, spiral galaxies, rotating stars, orbiting planets, is the visible pattern of those ancient imbalances, refined by gravity and time into the structures we recognize. When the first stars formed, their birth was anything but gentle. Vast clouds of gas collapsed under their own gravity, flattening into disks as they spun faster. In the centers of those disks, pressure and heat built up until nuclear fusion began, igniting the first starlight. Around those newborn stars, leftover material continued to rotate, forming swirling disks that eventually became planets. Each planet carried the imprint of that rotation, spinning as it cooled and solidified. The direction and speed of their spin depended on the random collisions and interactions that shaped them. Even moons that later formed from debris inherited the rotation of their parent bodies. In this way, spin became one of the most fundamental qualities of matter in motion. You can trace it backward from the rotation of the Earth to the cloud that formed the solar system, to the nebula that birthed the Milky Way, to the early fluctuations of the expanding universe. Each level hands its angular momentum down to the next, conserving the original motion that began at the dawn of time. There's a direct line of rotation connecting your turning planet to the first moment of cosmic asymmetry. Every spin, no matter how small, is part of that ancient inheritance. It's astonishing to think that the same principle governs both galaxies and electrons. On the larger scales, angular momentum defines the shapes of galaxies, the orbits of stars, and the stability of planetary systems. On the smaller scales, intrinsic spin defines the behavior of particles, influencing everything from magnetism to the chemistry of life. Spin is the thread that weaves together the cosmic and the quantum. It's not an accident of scale, it's a universal law. The formation of galaxies illustrates this beautifully. In the first few 100 million years, clouds of dark matter and gas began to collapse under gravity. As they did, they started to rotate, their rotation rates depending on how the surrounding matter was distributed. Over billions of years, these rotating clouds flattened into disks, forming spiral galaxies like our own. The Milky Way's elegant arms are not static structures. They are density waves moving through a rotating disk of stars. Every star, including the Sun, orbits the galactic center as part of that grand spin. Inside those galaxies, smaller rotations formed within larger ones. Stars developed planetary systems. Some of those planets developed moons. Each of these spins traces back to the same original source, the uneven distribution of mass and motion in the early universe. It's a fractal of rotation, repeating across scales, from cosmic to microscopic. Even the turbulence in interstellar clouds follows this pattern. Within a single star-forming region, there are eddies and swirls, tiny pockets of spin nested within larger flows. These create complex magnetic fields that help regulate the collapse of matter. Without those fields, stars might form too quickly or fragment into pieces. Spin stabilizes the process, slows it down, guides it toward balance. In a very real sense, rotation is what allows structure to exist at all. If you could watch the early universe evolve in fast forward, you would see motion emerging from apparent stillness, clouds twisting, filaments stretching, galaxies spiraling into shape. Each layer of structure owes its existence to the interplay between gravity and angular momentum. Where gravity tries to pull inward, spin pushes outward, spreading motion around, preventing collapse. This dance between attraction and rotation defines the shape of everything from stars to solar systems to galaxies. On even smaller scales, within the heart of matter itself, the concept of spin takes on a different meaning. Quantum spin isn't literal rotation, but a kind of intrinsic angular momentum built into particles. It determines how particles align with magnetic fields and how they combine to form atoms. The spin of electrons, for instance, dictates the structure of the periodic table, influencing the chemistry of everything we see and touch. Without spin, atoms wouldn't form stable shells. Without those shells, there would be no molecules, no solids, no life. So when we ask how cosmic spin began, we're really asking how the universe came to have structure at all. Motion and form are two sides of the same coin. The same laws that gave the universe its angular momentum also gave it shape, texture, and rhythm. The galaxies that rotate in slow, graceful spirals are not just moving. They're expressing the memory of those first fluctuations, the remnants of imperfection made visible through time. Even now, the universe continues to evolve through these interactions. Galaxies collide and merge, trading angular momentum like dancers swapping partners. Some stars are flung outward, while others sink toward the center. The result is often a new, more massive galaxy spinning at a slightly different rate. Nothing in this process ever stops. The total angular momentum remains constant, but its distribution shifts endlessly. The cosmic spin is not a relic of the past. It's an ongoing process, written into the fabric of reality. If you could hold the whole universe in your mind for a moment, you'd see it as a system in constant motion, every part turning, every scale echoing the same dynamic. The galaxies don't just move through space, they also twist space itself. Near massive rotating bodies like black holes, space-time is dragged along with the spin, bending light and time around it. Spin doesn't just move matter, it shapes the geometry of the universe. This connection between motion and geometry lies at the heart of modern physics. Space and time are not static backdrops for matter to move through. They are dynamic, interwoven fields that respond to motion and energy. When something spins, it doesn't just rotate within space, it affects space itself, altering how gravity behaves, how light travels, how time flows. The simple act of spinning becomes a way the universe expresses its own structure. And so, from the first quantum ripples to the turning of galaxies, the cosmic spin is both cause and consequence. It began as a whisper of asymmetry and became the language of existence. Every rotation, every orbit, every cycle is a continuation of that first moment when stillness broke and motion began. If you listen closely enough, through the hum of the planet beneath you, through the slow drift of the stars, you can almost sense it. The same motion that started everything is still here, moving through you, carrying you forward through time and space. The universe is not simply spinning. It is remembering how it began, over and over, in every atom, every orbit, every breath. Everything that spins, from the smallest particle to the largest galaxy, owes its motion to a principle so simple that it almost seems like common sense once you see it. The universe doesn't like to lose what it already has. When something starts rotating, it keeps rotating, unless something else interferes. That persistence is called angular momentum. It's not just a property of motion, it's one of the most deeply conserved quantities in nature, as fundamental as energy or charge. The birth of angular momentum wasn't a single moment or event. It was an inevitable outcome of how the universe behaves. It's the quiet, mathematical promise that motion, once begun, will endure. To understand where it comes from, you can start with something familiar. Picture a spinning coin. Once it starts, it resists stopping. You can hear its faint hum on the tabletop as it wobbles, its edges shimmering between order and collapse. The same thing happens when a planet turns, or a star, or a galaxy. Once the spin exists, it carries on, not because of any hidden force pushing it, but because no force is taking it away. Angular momentum is the measure of that persistence, the strength of rotation multiplied by how the mass is distributed around the axis of motion. It's a simple formula, but behind it lies the symmetry of the universe itself. The laws of physics are built on symmetries, patterns that stay the same even when you shift your perspective. Move a system around in space and its behavior doesn't change. Rotate it and the rules still hold. These symmetries, according to Noether's theorem, are what give rise to conservation laws. The symmetry of space under rotation is what gives birth to the conservation of angular momentum. In other words, the reason spinning things keep spinning is that the universe looks the same no matter which way you face it. That quiet uniformity of space is the reason motion endures. When the early universe began to cool and expand, particles and radiation filled space uniformly. But even then, that symmetry was not perfect. Tiny fluctuations gave rise to local motions, and wherever motion existed, angular momentum followed. The first hints of it appeared not as spinning galaxies or turning stars, but as quantum fluctuations. Minuscule imbalances in momentum that appeared and vanished in the fabric of space itself. The conservation of angular momentum ensured that whenever rotation appeared in one direction, an equal and opposite rotation appeared somewhere else. The total always balanced, but the local motions remained. The birth of angular momentum was not the creation of something new. It was the solidification of a rule the universe was already following instinctively. On the scale of atoms, angular momentum appears in two forms. The first is orbital, like the way electrons move around a nucleus. The second is intrinsic spin, a built-in property of particles themselves. Intrinsic spin isn't literal rotation. An electron isn't a tiny ball turning in space, but it behaves as if it were, carrying angular momentum that can interact with magnetic fields and determine how particles combine. The spin of electrons, protons and neutrons determines how atoms bond, how light is emitted, how energy levels form. Even at that scale, the universe expresses its preference for rotation. Angular momentum is woven into matter itself. As the universe expanded, the same principle scaled upward. Gas clouds gathered under gravity, and as they did, small random motions became organized into rotation. Imagine a massive cloud of hydrogen drifting through space. Its atoms are moving in all directions, colliding, scattering, exchanging energy. Over time, gravity pulls them inward, drawing them toward the cloud's center. But no collapse is ever perfectly straight. Some particles fall slightly to the side, some move faster than others. These tiny deviations add up, creating a small overall rotation. Conservation of angular momentum locks that rotation in. As the cloud shrinks, it spins faster, just as a figure skater does when pulling in their arms. The result is a disk of spinning gas, the birthplace of stars and planets. This process plays out again and again across the universe. The same law that keeps a skater turning keeps galaxies from collapsing. Angular momentum doesn't disappear when systems evolve. It changes form, spreads out, and rearranges itself. When a star forms, its rotation might slow slightly as it transfers some of its angular momentum to the surrounding disk. That disk, in turn, spins faster and flattens, giving rise to planets. Each step of the process is a negotiation. Motion passed from one form to another while the total remains unchanged. In a sense, angular momentum is the currency of the cosmos. Every collision, every orbit, every turn involves an exchange. When two galaxies collide, their spins combine, forming a new rotation that reflects both their histories. When a planet captures a moon, the system adjusts its motion to conserve the total. Even something as small as a comet swinging past a planet experiences a trade in angular momentum, altering its path and speed in subtle ways. Nothing happens in isolation. The universe keeps a perfect balance sheet, and angular momentum is one of the quantities it never lets drift out of order. To see how deeply this principle runs, you can look to the stars themselves. A young star rotates quickly, its surface completing a turn in hours or days. Over time, as it radiates energy and emits streams of charged particles in the solar wind, it loses some of that momentum. The lost angular momentum transfers to the particles that escape, which carry it away into space. The star slows down, but the total angular momentum remains the same. It's simply spread thinner, dispersed into the interstellar medium. That balance continues indefinitely. The rotation of one object always depends on the rotation of the things around it. Even in death, stars obey the same rule. When a massive star collapses into a neutron star, its radius decreases dramatically. The mass stays roughly the same, but the spin accelerates. Angular momentum is conserved, so the smaller the radius, the faster the rotation. That's why neutron stars can spin hundreds of times per second, and why black holes can rotate at speeds approaching the speed of light. The smaller and denser an object becomes, the more its angular momentum is concentrated. The principle never breaks, no matter how extreme the conditions. It's humbling to think that a law so simple can hold across such vast differences of scale. From the subatomic to the cosmic, the rule is the same. Rotation persists unless something external intervenes. And in the near-perfect emptiness of space, there's almost nothing to slow it down. Planets keep spinning for billions of years. Stars keep turning long after their light fades. Galaxies rotate through time itself, their motion so steady that it becomes a kind of heartbeat for the universe. Angular momentum also shapes how systems evolve dynamically. The orbits of planets are stable because their angular momentum balances the pull of gravity. If a planet moves closer to its star, it speeds up. If it drifts farther away, it slows down. That exchange keeps the orbit consistent, a delicate interplay between energy and motion. Without angular momentum, the orbits would decay, the planets falling inward or flinging outward uncontrollably. The stability of the solar system, and of systems everywhere, depends on this invisible accounting. The same balance applies to galaxies. Stars orbit the galactic centre because their angular momentum counteracts gravity's pull. If a star loses angular momentum through friction, collisions or interactions, it drifts inward. If it gains momentum, it moves outward. This slow migration of stars helps galaxies evolve, redistributing mass over billions of years. Even the spiral arms of galaxies, those luminous swirls of starlight, are shaped by angular momentum. They are not fixed structures, but density waves, patterns that move through the disk as stars orbit. Angular momentum keeps those patterns coherent, turning chaos into symmetry. In more familiar terms, you experience angular momentum every time you ride a bicycle or sit in a rotating chair. You can feel how the spin resists change. Try to stop it suddenly and it pushes back. Turn it slightly and it fights to stay aligned. That resistance is the same principle, keeping the Earth's axis stable. The planet's angular momentum acts like a gyroscope, maintaining its orientation even as it moves through space. The slow precession of that axis, a gentle wobble over thousands of years, is a reminder that even the most stable systems are still in motion, still negotiating with the universe's forces. On a deeper level, angular momentum reveals something profound about time. A system that spins is a system that remembers. The direction and speed of rotation carry information about how it formed, what it has interacted with, and what forces have acted upon it. A galaxy's spin encodes the distribution of matter in its early history. A planet's rotation tells the story of its collisions and accretions. Even the tilt of the Earth axis is a fossil of its past encounters. Angular momentum is memory made mechanical, written in the language of motion. It also hints at the limits of human perspective. We tend to think of movement as something we cause or control, but angular momentum reminds us that motion is older and deeper than intention. The same law that governs the spin of a toy top also governs the orbit of the moon and the rotation of the sun. The human act of spinning an object is just another expression of a rule that predates stars. The universe doesn't need consciousness to move. It moves because that's what balance demands. If we could somehow remove all external forces and let the universe evolve untouched, angular momentum would keep every object turning forever. But in reality, interactions are constant. Tidal forces, magnetic fields, collisions, and radiation gradually redistribute angular momentum. The total stays the same, but its arrangement changes endlessly. The universe never loses its rotation. It just moves it around like a current flowing through an ocean without shores. Even the expansion of the universe interacts with this principle. As galaxies drift apart, their local angular momentum stays conserved. The stretching of space doesn't dilute rotation. Instead, it isolates it, allowing each region to maintain its internal motion. That's why galaxies can keep spinning even as they recede from one another faster and faster. Angular momentum operates locally, but its law is universal. There's a subtle beauty in how angular momentum connects the tangible and the abstract. You can measure it, calculate it, see its effects, but you can also feel it intuitively. The steadiness of a turning wheel, the calm of a balanced orbit, the persistence of a spinning planet, all are manifestations of the same invisible order. It's the universe's way of saying that motion, once given, is never forgotten. In human experience, that continuity has an almost emotional resonance. We find comfort in things that turn rhythmically. The tick of a clock, the rotation of the seasons, the repetition of waves on the shore. Those patterns mirror the physical laws that govern everything else. They remind us that while the world changes constantly, it does so within boundaries that remain steady. Angular momentum is one of those boundaries. It's the quiet rule that keeps the universe coherent through time. If you look closely at the night sky, every point of light tells part of that story. Each star spins, each planet turns, each moon keeps its rhythm. The balance between gravity and angular momentum defines where they are and how they move. The visible universe is the expression of that balance frozen in motion, and beneath it all, the same conservation continues, unbroken since the first moment. In the end, angular momentum is not just about rotation, it's about continuity, about the way the universe maintains its own memory through time. Every turn, every orbit, every spin is a line connecting past to present. The birth of angular momentum wasn't a single event, but an ongoing process. The universe, learning the simplest and most enduring rule it ever created. Once you begin to turn, you never truly stop. And so, as matter continued to gather and rotate, as clouds collapsed into stars and stars into systems, the ancient rhythm of rotation deepened. The spin became structure, the motion became form. Out of angular momentum, the universe found its way toward complexity, toward the first luminous stars and the swirling disks that would become home to worlds like ours. The universe at its beginning was quiet in a way that no silence on Earth could ever match. It wasn't the kind of quiet you hear before dawn, or the pause between heartbeats, but the deep and vast absence of anything recognizable. A darkness filled with the thinnest traces of matter, drifting endlessly. Hydrogen and helium, the two simplest elements, made up almost everything that existed. They floated freely in a cosmos still cooling from its birth, a vast sea of invisible gas waiting to take shape. For millions of years, nothing much seemed to happen. The universe expanded, thinned and darkened, a faint afterglow fading slowly into black. Yet within that apparent stillness, something was beginning to stir. Gravity, patient and relentless, had been at work since the beginning. It doesn't shout or rush. It pulls softly but steadily, always in the same direction, inward. Where there was slightly more gas than average, gravity's pull was a little stronger, and that tiny difference made all the difference. Over immense spans of time, those denser patches began to draw in their surroundings, attracting more atoms, more mass, more weight. Slowly the great clouds of gas that would become stars began to form. They started as faint smudges of density, invisible to the eye but filled with potential. At first, the gas in these primordial clouds moved randomly. Each atom followed its own path, colliding occasionally, bouncing, exchanging energy. But randomness never stays truly random. Patterns emerge as gravity gathers the scattered pieces together. The pull isn't uniform. There are always tiny irregularities, asymmetries, places where the gas is denser or thinner, moving slightly faster or slower. Those irregularities twist the flow. They cause the collapsing cloud to start rotating. Once that happens, the motion cannot be undone. Angular momentum takes hold. The cloud begins to twirl. It doesn't twirl quickly at first. The motion is slow, almost imperceptible compared to the vastness of the cloud itself. But as gravity continues its work, drawing matter inward, the cloud's spin accelerates. The reason is simple. As the cloud shrinks, its radius decreases, and with angular momentum conserved, the rotation must speed up. It's the same principle that makes a skater spin faster when drawing in their arms. The result is a slow, elegant transformation, a diffuse sphere of gas turning into a flattened, spinning disk. The universe was learning its first dance steps. This process, repeated across space and time, became the fundamental mechanism for building structure. Every star, every planet, every moon traces its origins back to one of those turning clouds. They are the wombs of creation, and their twirling motion is what allows them to organize chaos into order. Without spin, a collapsing gas cloud would simply fall inward until it became a featureless sphere. But with even a trace of angular momentum, the story changes entirely. Rotation redistributes the collapsing material, creating a balance between gravity's pull and the outward push of motion. It's that balance that allows stars and planets to form. Inside a rotating gas cloud, not everything falls direct to the center. The particles moving along the plane of rotation settle into orbit, circling around the densest region. Over time, this forms a flat, rotating disk. In the middle, where the density and pressure are highest, matter continues to collapse, heating up as it falls inward. Eventually, it becomes hot enough for nuclear fusion to ignite, and a star is born. Around that newborn star, the remaining material continues to spin, gradually cooling and condensing into smaller bodies. These are the beginnings of planets, asteroids, and moons, all shaped by the same motion that began when the cloud first learned to turn. The moment a star ignites, the balance inside the cloud shifts. The light and wind from the newborn star push back against the surrounding gas, clearing away much of the remaining material. But the spin remains. The planets inherit their orbits and rotations from that initial angular momentum. The direction they move, the tilt of their axes, even the speed of their days, all of it is written in the cloud's original spin. In a very real way, every world carries the fingerprint of its parent nebula, a record of how the gas once twirled in the dark. These clouds of gas are not small. The ones that form stars can stretch across light years, containing enough material to make thousands of suns. They are enormous, but they are also delicate. The balance between gravity, pressure, and motion is finely tuned. If the cloud rotates too fast, it won't collapse. It will spread out and dissipate. If it rotates too slowly, it will collapse too quickly and fragment into chaos. But nature finds the middle ground. The interplay between these forces creates stability. The cloud collapses just enough to form stars, but not so much that it destroys itself. It's a process of negotiation, a cosmic conversation between motion and gravity. As the cloud contracts, the conservation of angular momentum ensures that no motion is lost. Even the smallest eddies, the local swirls and twists within the larger rotation, play a role. They concede the formation of multiple stars, each with its own disk, each with its own spin. In the densest regions of space, where clouds overlap and interact, entire clusters of stars form together, all spinning in slightly different directions. Over time, these clusters drift apart, their stars carrying the memory of their shared origin like family resemblances scattered across the sky. You can still see these clouds today, glowing faintly in the night sky. The Orion Nebula, the Eagle Nebula, the Carina Nebula, they're all vast nurseries of gas and dust, where gravity and spin are shaping new generations of stars. Telescopes capture their beauty in images of colour and light, but what those pictures don't show is the slow, relentless motion beneath. Each glowing filament, each swirling tendril, is moving. The gas flows, compresses, twists, and turns. The patterns we see frozen in photographs are only snapshots of a process that unfolds over millions of years. If you could watch one of these clouds in accelerated time, you'd see a ballet of formation. The diffuse gas begins to gather, the bright knots of new stars appear, the surrounding material flattens into rotating disks. Out of chaos comes order, not because of design, but because motion and gravity demand it. Every spin, every orbit, every rotation is a compromise between the inward pull of mass and the outward momentum of motion. The cloud doesn't just twirl by chance. It twirls because that's the only way it can survive the collapse. Angular momentum is the silent architect of this process. Without it, the gas would have nowhere to go but down. With it, matter finds a path to balance. The spinning disk distributes material, regulates collapse, and creates a space where complexity can emerge. It's this same dynamic that gives rise to planets, to moons, to rings, to the ordered chaos of the solar system. Every cloud that learns to spin becomes a cradle for structure. Within those rotating disks, smaller vortices appear, regions where gas and dust clump together under their own gravity. These are the seeds of planets. As they orbit, they collect more material, growing larger and denser. Collisions are frequent but not random. The shared direction of motion keeps everything roughly aligned. Over time, the disk thins and clears, leaving behind a system of planets orbiting a central star, each turning on its own axis, each preserving the memory of the original rotation. What's remarkable is that this pattern repeats everywhere. Whether you look at a small protostar in a nearby cloud or a massive spiral galaxy billions of light years away, the same physics applies. The universe builds itself through rotation. The shapes we see, disks, rings, spirals, are all signatures of angular momentum at work. It's one of the reasons the cosmos has such coherence. Despite its vastness and variety, everything follows the same quiet rule. Motion persists. The story of these twirling clouds is also a story of transformation. Gravity and rotation don't just create structure, they create energy. As the gas collapses and spins faster, it heats up, emitting radiation that can travel across light years. That light carries information about the cloud's motion. By studying the spectral lines of that light, astronomers can measure how fast different parts of the cloud are moving, how they rotate, how they twist. Every wavelength tells a piece of the story, of the chemistry, the temperature, the turbulence. It's like listening to the heartbeat of a forming star. And there's something poetic in the fact that the universe's most dynamic processes unfold at a pace almost too slow to imagine. The twirling of a cloud that gives birth to a star might take tens of millions of years. The motions are steady, deliberate, patient. Nothing rushes. The gas follows the path set by gravity and conservation, and the result is elegance, not the elegance of design, but of inevitability. The universe doesn't need to plan beauty. It arises naturally from the way motion and matter interact. When you look at the Milky Way on a clear night, the faint band of light stretching across the sky is the sum of countless such processes. Each star in that band began as a spinning cloud. Each of those clouds was shaped by the same laws. The patterns we see are echoes of the first motions that began billions of years ago. The entire galaxy is a memory of those early twirls scaled up to cosmic proportions. What began as a diffuse haze of hydrogen became a structured universe through nothing more than motion and time. The clouds that learned to twirl gave rise to everything else. Stars that burn, planets that orbit, moons that shine. Without that first rotation, there would be no galaxies, no suns, no Earth. Even the air you breathe and the water that moves through your body are made of atoms forged in spinning stars that once formed from twirling gas. Every part of your existence is built on the remnants of that motion. If you could trace your own atoms backward through time, you'd find yourself in one of those clouds drifting among hydrogen and helium, moving in slow spirals as gravity began to take hold. You'd be part of that first cosmic spin, long before planets or people existed. And you'd keep spinning still through every transformation, through every layer of creation, because angular momentum never truly disappears. It's carried forward endlessly, changing form but never fading. The universe never stopped learning to twirl. It just found new ways to express the same rhythm. In galaxies, in stars, in planets, in atoms, the spin continues. Long before the Earth had oceans or air, before there was even a sun to rise and set, a vast cloud of gas and dust was turning slowly in the cold dark of space. It was one of many such clouds, formed from the remains of older stars that had lived, burned and died, scattering their contents outward into the interstellar void. Inside that cloud was the faint residue of everything that had ever been. Hydrogen from the Big Bang, carbon and oxygen from ancient supernovae, heavier elements from the hearts of long-forgotten giants. It drifted silently, but it was not still. The cloud was turning, drawn inward by gravity, held in check by its own spin. In that balance of collapse and motion, the story of our solar system began. The rotation of the cloud was almost imperceptible at first. Measured on human scales, it would have seemed motionless, but across light years of space, even the faintest rotation becomes meaningful. As the gas contracted under gravity, its rotation increased. The Conservation of angular momentum made sure of that. The more tightly the material fell inward, the faster it spun. In time, what had once been a vast, shapeless cloud became a flattened disk of gas and dust rotating steadily around a growing core. That core, dense and hot, was the young sun. The surrounding disk, known as the solar nebula, was the cradle of everything that would come after. It stretched far beyond where the outermost planets would eventually orbit, filled with swirling eddies and currents of gas. Tiny grains of dust collided, stuck together and grew. Each fragment carried its own bit of angular momentum, inherited from the larger rotation of the disk. With every collision, the motion became more organized. The fragments formed clumps, and the clumps became planetesimals, the seeds of worlds. Closer to the young sun, where temperatures were higher, only metals and rock could survive. These materials gathered into the small, dense planets that would become Mercury, Venus, Earth, and Mars. Farther out, where the cold allowed ice to remain solid, giant planets formed, pulling in massive amounts of gas from the surrounding disk. Jupiter and Saturn grew first, their gravity carving paths through the nebula. Uranus and Neptune followed, smaller and slower, their orbits defined by the giants that came before. The entire structure, from the innermost orbit to the outermost edge, was a single, rotating system, a vast celestial waltz choreographed by gravity and angular momentum. Every piece of this system moved in harmony. The planets all orbited the sun in nearly the same plane, travelling in the same direction as the disk had spun. Even the moons that would later form around those planets inherited that motion. The regularity of it is striking. Not random or chaotic, but precise, rhythmic, almost musical. The solar system moves as though it remembers a dance learned long ago, each orbit timed to the same beat. If you could stand outside it all and watch from afar, you'd see a scene both simple and extraordinary. The sun burns steadily at the centre, its light spilling outward. Around it, the planets trace their paths, Mercury darting close in tight, rapid circles, Venus following smoothly behind, Earth gliding along its slightly tilted orbit, Mars further out, its path slower, more deliberate. Beyond them, the giant planets move in wide, sweeping arcs. Jupiter, the massive dancer, carries with it more momentum than all the other planets combined, its gravity subtly shaping the rhythm of the entire system. Saturn, adorned with rings of ice and dust, turns with quiet grace. Farther still, the faint light of Uranus and Neptune marks the outer edge of the solar stage. All of this motion began with that original spin, and it continues with near-perfect fidelity. The planets have danced their paths for billions of years, almost unchanged. The same rules that set them in motion at their birth still govern their movements now. Every orbit, every rotation, every tilt of an axis is the direct consequence of that first twirl in the solar nebula. The waltz began before the Earth even existed, and it hasn't missed a step since. Yet the system is not entirely smooth. The motions contain small irregularities, gentle improvisations that give the dance its character. The planets tug on one another as they move, their gravity bending each other's paths ever so slightly. These subtle interactions, accumulated over millions of years, create variations in orbits, eccentricities, inclinations, resonances. Jupiter and Saturn, the two largest partners, exchange momentum in a rhythm that affects even the farthest reaches of the system. The smaller planets, like Earth, are constantly adjusting their steps, their orbits shifting minutely in response. It's a dynamic, ever-evolving pattern, perfectly stable yet endlessly changing. The formation of the planets themselves is a story of collisions, countless impacts, some gentle, some violent. When two growing worlds collided, their angular momenta combined. Sometimes the result was stable, a new planet spinning with the merged momentum of its parts. Sometimes it was catastrophic, scattering debris that would later reassemble into moons or rings. The Earth likely gained its moon in one such impact, when a Mars-sized body struck it early in its history. The collision was cataclysmic, but even that chaos followed the same rules. The debris that flew into orbit settled into a disk, and from that disk, the moon formed. The direction of its orbit and the tilt of Earth's axis both preserve the memory of that event. Even destruction in this system produces motion that endures. As the planets grew and the disk of gas thinned, the young sun continued to mature. Its magnetic fields interacted with the remaining gas, transferring angular momentum outward. The star itself rotated quickly at first, but gradually slowed as its magnetic wind carried away energy. The planets, by contrast, kept most of their spin. Their orbits stabilized, their paths cleared. What remained was a system in delicate equilibrium, each planet balancing the pull of gravity with the inertia of its motion. The waltz had reached its full rhythm. Over time, this rhythm became the foundation for everything that followed. The rotation of the Earth set the length of a day. Its orbit defined the year. The tilt of its axis created the seasons. The moon's gravitational pull shaped the tides. Every pattern of motion that structures life on this planet. Day and night, the changing of seasons, the rhythm of growth and rest. All of it arises from the ancient spin of the solar nebula. The daily and yearly cycles we take for granted are the faint echoes of a dance that began before life itself existed. It's easy to forget that these movements are not static. The planets don't follow perfect circles, and their rotations are not unchanging. The Earth's spin is gradually slowing, its days lengthening by fractions of a second over centuries. The Moon, moving farther away each year, carries angular momentum outward as it drifts. Jupiter's immense gravity gently influences the paths of asteroids and comets, sending some inward toward the Sun and flinging others out into interstellar space. The solar waltz is precise, but it's also alive. The steps evolve as the dancers interact. If you could speed up time, the solar system would look like a slow whirlpool of light and motion. Planets would trace glowing ribbons around the Sun, moons would weave smaller loops around their planets, and comets would arc in long, sweeping paths before disappearing again into the dark. From a distance, it would seem almost serene, a luminous pattern unfolding endlessly in 3 dimensions, every motion connected, every turn accounted for. What's most remarkable is how stable the pattern remains. The balance between gravitational attraction and angular momentum keeps everything in motion without collapse or escape. The Sun's mass provides the anchor, and the planet's momentum provides the counterweight. It's a relationship of perfect tension, not static, but sustained. The same principle that keeps a spinning top upright keeps the planets in their orbits. It's the interplay of gravity and motion that defines harmony on a cosmic scale. The waltz also extends beyond the planets themselves. Countless smaller bodies join the dance. Asteroids, comets, dwarf planets, and rings. The asteroid belt between Mars and Jupiter is a relic of an earlier stage, a region where the pull of Jupiter's gravity prevented a planet from forming. The objects within it orbit the Sun in their own synchronized rhythm, a million silent dancers keeping pace with the greater motion around them. Beyond Neptune, the Kuiper belt holds icy remnants from the solar system's birth. Frozen in time, but still following their inherited paths. Even the distant Oort cloud, a sphere of icy bodies surrounding the system, is part of the same choreography, bound to the Sun by gravity's faint but persistent pull. All of this movement might seem chaotic from within, but from afar it becomes a kind of order. The structure of the solar system reflects a fundamental truth about motion itself. Stability is not stillness. It's balance within motion. The planets remain where they are not because they resist movement, but because their movement is perfectly tuned to the forces acting on them. If they moved any slower, they would fall inward, any faster, and they would fly away. Their orbits are the precise compromise between falling and escaping. That compromise is what creates beauty. Even the diversity of spins among the planets tells part of this story. Each world rotates at its own pace and tilt, shaped by its unique history. Jupiter spins once every 10 hours, flattening slightly at the poles under the force of its rapid rotation. Venus turns so slowly that its day lasts longer than its year, and in the opposite direction to most of the other planets. Uranus spins almost on its side, as if knocked over by some ancient collision. Earth, tilted at just the right angle, turns every 24 hours, its axis wobbling slowly over thousands of years. These differences are the improvisations within the larger dance, each planet keeping time in its own way. The waltz continues in silence. There is no music to hear, but there is rhythm everywhere. The gravitational interactions between planets create periodic resonances, subtle patterns that repeat over time. Jupiter and Saturn, for instance, align roughly every 20 years as beat that echoes through the architecture of the system. These resonances can stabilize or destabilize orbits, depending on their timing. Some have persisted for billions of years, locking moons and planets into synchrony. Others shift slowly, changing the dance's tempo as time unfolds. The motion of the solar system also connects to the broader motion of the galaxy. As the planets orbit the Sun itself moves around the Milky Way, completing one galactic revolution every 230 million years. The planets, bound to the Sun by gravity, move with it, carried through space like dancers gliding across a vast and invisible floor. The solar waltz, intricate and contained, is part of a far greater performance than the turning of the galaxy itself. From our small place within it, we experience this motion without ever feeling it. The ground beneath us feels steady, the sky serene. Yet we're moving through space at unimaginable speed, carried by the combined rotations of Earth, Sun, and galaxy. The stillness we perceive is an illusion born of perfect participation. We move with the music, and so we do not hear it. When you look up at the stars at night, you're watching the solar waltz unfold from within. The constellations shift subtly from hour to hour, from season to season, because the Earth turns and orbits. The Sun rises, sets, and returns because of that same motion. The planets wander across the sky, each following its rhythm. Even the path of light itself is shaped by the geometry of this rotation. Every moment of day and night is a step in a dance that has continued unbroken for 4.5 billion years. And though we measure these motions with precision, calculating orbits, predicting eclipses, tracking the paths of comets, the underlying pattern remains simple. Matter in motion stays in motion. Gravity holds it together. Angular momentum carries it forward. The solar system endures because it follows the rules that began at the dawn of time. The same principles that guided the first spinning cloud still govern the turning of our world. If you could pause it all for just a second, freeze the planets in their orbits, the moons in their paths, the comets in their arcs, you'd see a structure of breathtaking geometry, a pattern of circles and ellipses nested within one another, each orbit a thread in a web of motion. But the beauty of it lies not in the still image, but in the movement itself. The solar waltz exists only because it never stops. The balance holds because everything continues to turn. From the slow rotation of Saturn's rings to the quick flicker of a day on Jupiter, from the whisper of a comet's tail to the steady spin of the Sun, the motion unites all parts of the system. The dance has no beginning or end, only continuity, a rhythm that stretches backward to the spinning clouds that formed it, and forward to whatever shapes will follow. The same laws that began the motion will keep it going, quietly, gracefully, endlessly. And as the planets continue their orbits, carrying with them their moons, their seasons, their histories, the solar waltz turns on. Each step is both ancient and new, each rotation a repetition of the first. From the perspective of deep time, it is one long, unbroken movement. The universe remembering how to turn, expressed through the dance of a single star, and the worlds that follow it through the dark. The world turns so quietly that you would never know it from standing still. The ground feels solid beneath your feet. The horizon holds its place. The air doesn't rush past in a blur. Yet in every moment the Earth is spinning at a speed that would make sound and sight impossible if we could feel it. At the equator, our planet rotates at roughly 1,000 miles per hour, but everything around us, air, water, land and life, moves with it. There is no friction against the sky, no wind of motion to give us away. The spin is invisible, but it defines everything we experience. This turning began long before there was a sky to watch or an ocean to reflect it. When the Earth first formed from the spinning disk around the young sun, it inherited its rotation from that large motion. The planet grew through countless collisions, each one a violent exchange of energy and momentum. With every impact, its spin changed slightly, sometimes faster, sometimes slower, sometimes tilted a little more or less. By the time it settled into the orbit we now occupy, the Earth had found a steady rhythm, turning once every few hours. It has been slowing ever since, but never stopping and never still. The cause of that gradual slowing lies just above us. The moon, forever circling our planet, tugs on the oceans with its gravity. The water rises and falls in tides that sweep across the surface, shifting billions of tons of mass from place to place. That movement creates friction between the sea and the land, draining a tiny fraction of Earth's rotational energy each day. The effect is barely noticeable, only a few milliseconds added to the length of a day every century, but over geological time, it matters. Hundreds of millions of years ago, a day on Earth lasted less than 20 hours. In the deep future, it will last longer still. The moon, in return, is slowly moving away, about 1.5 inches farther each year. The two are locked in a slow exchange of motion, an invisible dance that has lasted since the beginning. Even with that gentle deceleration, the Earth's spin remains remarkably stable. The rotation defines the shape of the planet itself. The centrifugal force caused by spinning pushes outward at the equator, flattening the poles slightly. The Earth is not a perfect sphere, but an oblate one, wider at its middle. This shape is what allows gravity to vary slightly across its surface, making the weight of an object fractionally different at the poles than at the equator. The planet's bulge also affects its orientation in space, contributing to the slow wobble known as precession, a subtle 26,000-year cycle that causes the direction of Earth's axis to drift gradually, like a top that turns smoothly but never points in quite the same direction forever. That wobble changes the stars we see in the night sky over millennia. The North Star, which now sits almost perfectly above our pole, will drift away in time and new stars will take its place. To anyone living their entire life within a few generations, the sky seems fixed, eternal. But across epochs, even the heavens follow the rhythm of the Earth's turning. The slow pirouette of our axis rewrites the map of the stars, turning constellations like gears in a cosmic clock. The rotation of the planet is not only a matter of geometry or physics, it is the foundation of life's patterns. Every organism on Earth has evolved the cadence of day and night. The rising and setting of the sun, the alternation of light and dark governs the rhythms of behavior, metabolism and growth. The circadian cycle, that internal clock within nearly every living cell, is an echo of the Earth's rotation written into biology. Plants open and close their leaves according to it. Animals wake, feed, and rest by its signal. Even humans, with our electric lights and digital hours, still feel its pull. The body's chemistry shifts through the day, hormones rising and falling in tune with the turning of the world. The planet's rotation isn't just a physical motion, it's the metronome of life. And yet, for something so central, the Earth's rotation is neither perfectly smooth nor entirely predictable. The planet's interior, with its molten outer core and solid inner core, moves in complex ways. As that liquid metal flows, it subtly alters the planet's moment of inertia, changing how fast it spins. The shifting of the atmosphere, the circulation of the oceans, Even the melting and freezing of ice all redistribute mass, causing minute fluctuations in the rotation rate. Scientists can measure these variations to fractions of a millisecond. They are tiny, but they reveal how alive the planet really is. Not static, but breathing, flexing, adjusting. Every rotation brings with it invisible consequences. The spin of the Earth generates the Coriolis effect, a force that deflects moving air and water, shaping the circulation of the atmosphere and the currents of the seas. It's what makes hurricanes spin, what organizes weather into patterns that repeat across latitudes. Without that spin, the winds would simply blow straight from hot to cold, and the oceans would move in direct lines between poles and equator. The Earth's pirouette turns chaos into structure, disorder into rhythm. Even the magnetic field that protects the planet from solar radiation owes its existence to motion. Deep inside the Earth, molten iron flows around the solid core, and the planet's rotation helps organize that flow into a vast self-sustaining dynamo. The movement of charged particles creates magnetic lines that extend far into space, forming a shield against the solar wind. Without the Earth's spin, that dynamo would fade, the field would collapse, and the atmosphere could be stripped away by radiation. The rotation is not just a motion, it's a defense, a life-sustaining engine that runs silently beneath our feet. From space, the Earth's spin is breathtaking. Astronauts who orbit the planet see entire continents pass beneath them every hour. Sunrises and sunsets happen 16 times a day from their vantage point. The planet below appears alive, a glowing marble turning through shadow and light. The movement of clouds, the shifting of weather systems, the changing colours of oceans and land, all of it unfolds in a steady rhythm. From that height, the planet's rotation becomes visible not as a concept, but as a living, continuous reality. It's easy to think of the Earth's rotation as constant, but in the language of deep time, nothing remains the same. The slowing caused by tidal friction will continue. The drift of the moon will widen its orbit. The planet's internal processes will evolve. Yet these changes happen so slowly that to human perception, they are indistinguishable from permanence. A day now lasts just long enough for the world to breathe, for the light to warm one side and the dark to cool the other. It's a balance that sustains the atmosphere, the climate, and the life within it. That balance is fragile. A faster rotation would create stronger winds, more extreme weather and shorter nights. A slower one would stretch the cycle of heat and cold, changing the rhythm that all living things depend on. The Earth's current speed is just right, not by design but by the natural convergence of physics and time. The same forces that shape the solar system gave us this precise rotation, this measured turn that allows life to flourish. It's another reminder that our existence is tied to motion at every level. The direction of the spin, too, tells a story. The Earth rotates from west to east, which is why the sun appears to rise in the east and set in the west. This direction is inherited from the rotation of the solar nebula, the same spin that set all the planets in motion around the sun. Most of the planets share this direction, though not all. Venus and Uranus rotate differently, their spins reversed or tilted by ancient collisions. But Earth's orientation, though slightly askew, has remained steady enough to preserve the rhythm of day and night as we know it. That tilt, about 23.5 degrees, is another gift of motion. It gives us the seasons, the slow breathing of the planet's climate. When the northern hemisphere leans toward the sun, it becomes summer there and winter in the south. 6 months later, the balance reverses. This gentle oscillation, caused by the geometry of the Earth's rotation, ensures variation without chaos. The seasons are a form of motion within motion, an interplay between spin and orbit that has shaped life for billions of years. Even the length of the day has been sculpted by these dynamics. The interplay between the Earth's rotation, the Moon's orbit, and the Sun's gravitational influence defines not only the passage of time but the structure of calendars, tides, and ecosystems. Every creature that hunts, sleeps, or migrates does so according to patterns created by that turning. The spin of the planet sets the tempo for the living world, an ancient rhythm we've followed unconsciously since the first single-celled organisms drifted in the oceans. If you could stand outside time and watch the Earth's entire history unfold in moments, you'd see the spin slowing imperceptibly, the moon inching away, the continents drifting under the pull of plate tectonics, the axis wobbling gently. It would look like a slow-motion dance, a pirouette without an end, always changing but never breaking form. The planet's surface might shift, its climates might evolve, but the motion would continue, unbroken. In a way, that spin is the closest thing to permanence the planet possesses. Mountains rise and erode, oceans form and vanish, species appear and fade, but the rotation endures. It has turned through every extinction, every revolution, every dawn. It is the one motion that unites every era of the Earth's story. When you stand on the shore and watch the sun dip below the horizon, what you're really seeing is not the sun moving at all, but the Earth itself turning gracefully into night. That quiet turn connects every living thing. Every heartbeat, every breath, every wave is synchronized to the planet's rotation. Even the cycles of sleep that define our daily lives are small reflections of this motion. We rest because the world turns. We wake because the light returns. The rotation isn't just background physics, it's the heartbeat of experience itself. The Earth's pirouette will go on long after the continents have changed their shapes, long after the last traces of current civilization are gone. The oceans will rise and fall in new patterns. The sky will tilt differently. The moon will drift farther away until its pull no longer slows the Earth significantly. Yet even then the planet will still turn, slower, quieter, but turning still. The spin will endure because the universe doesn't forget motion once it begins. The angular momentum that started in the solar nebula remains within the Earth, passed down through time like a pulse that never stops. We live inside that motion, carried by it, shaped by it, and though it feels like stillness, it is motion that gives us stability. If you step outside on a calm night, when the stars are sharp and the wind has settled, it's easy to imagine that the world is at rest. But if you wait, even for a few minutes, the stars will shift. The constellations will slide subtly toward the horizon. The Earth will have turned, quietly, invisibly, carrying you with it. The stillness you feel is only a perfect synchronization with the motion that holds you. The pirouette continues, smooth and unending. The same movement that began billions of years ago, still spinning beneath your feet, still shaping everything that is. And as the planet turns, drawing the next sunrise closer with each moment, the motion connects seamlessly to everything beyond it. The pull of the moon, the orbit around the sun, the rotation of the galaxy itself. The Earth's dance is not isolated. It is one step in a larger choreography, part of the same motion that began when the first clouds of gas learned to twirl, when the first light appeared, when the universe itself began to spin. The moon has always been there, or at least it feels that way. A pale companion in the night, steady, familiar, never quite the same from one evening to the next, but always recognizable. It drifts above oceans, forests and cities, watching silently as the Earth turns beneath it. We see its phases change, thin crescent, half full, and we mark time by its cycles without ever feeling its pull. Yet that pull is constant. It is the quiet connection that binds our world to its satellite, shaping tides, stabilizing the planet's tilt and gradually rewriting the rhythm of days. The moon's presence may seem gentle, but its influence reaches into the very structure of the Earth's motion. When the Earth was young, it spun fast and its surface was a molten sea of rock. In that chaos, something enormous happened, a collision so vast it reshaped the planet forever. A Mars-sized body, one of the many that roamed the early solar system, struck the Earth at a glancing angle. The impact was catastrophic. The outer layers of both bodies vaporized, flung into orbit as a glowing ring of molten debris. Gravity did what it always does. It gathered. Over time, that debris coalesced into a sphere. That sphere became the Moon. The Earth that emerged from that collision was different, larger, tilted, and spinning faster than before. The Moon, born from its outer layers, carried away a fraction of the planet's angular momentum. The two have been connected ever since, orbiting a shared centre of gravity deep within the Earth's interior. Their relationship is not static. It's a long, slow exchange of motion, a gravitational conversation that has lasted for more than 4 billion years. The pull between them is what we call the tide. On the side of Earth closest to the Moon, gravity draws the ocean slightly upward, creating a bulge of water that moves as the Earth turns. On the opposite side, another bulge forms, caused not by direct pull but by inertia, the tendency of water to continue moving as the planet and Moon orbit their shared centre. As the Earth spins, these bulges shift across its surface, creating the rhythmic rise and fall of the sea. The tides are the most visible reminder of the Moon's tug, a steady breathing of the planet that never stops. But the tide is not perfectly aligned with the Moon. The bulges are carried slightly ahead of the line connecting the two bodies, pulled forward by the Earth's faster rotation. That small offset matters. The extra mass of the tidal bulge exerts a gravitational pull on the Moon, accelerating it in its orbit. As the Moon gains momentum, it drifts slowly outward, about 1.5 inches farther away each year. At the same time, the drag of the tides on Earth's surface transfers energy from the planet's rotation, causing it to slow. Days grow imperceptibly longer. The balance of motion remains perfect. As the Moon gains orbital energy, the Earth loses rotational energy. Nothing is lost, it's merely exchanged. If you could watch this process sped up by millions of years, it would look like a slow dance in which the partners drift apart, moving in wider and wider circles. In the beginning, the Moon was much closer, looming large in the sky, tides rising hundreds of feet high and racing across the continents. The Earth spun once every few hours, the nights short and restless. Over time, the Moon's retreat and the Earth's deceleration tamed the chaos. The tides softened, the spin slowed, the dance found its equilibrium. What we experience now, the gentle rhythm of oceans rising and falling twice a day, is the calm after billions of years of gravitational dialogue. Even so, the exchange continues. The Moon's orbit grows wider, and the Earth's rotation slows further. Someday, billions of years from now, if the system were left untouched, the Earth and Moon would reach a state called tidal locking. The same side of Earth would always face the Moon, just as the same side of the Moon already faces us. From the planet's surface, the Moon would hang fixed in the sky, never rising or setting, while one half of the world would live beneath its constant gaze, and the other in perpetual absence of it. The oceans would still move, but differently, slower, deeper, more symmetrical. Time itself would stretch with the lengthened days. The Moon is already tidally locked to Earth. It rotates once per orbit, keeping the same face turned toward us. That's why we never see its far side from the ground. The synchronization happened long ago, when the Moon's own tides, raised by the Earth's stronger gravity, slowed its spin. Now, as the Moon drifts away, it keeps that locked rhythm perfectly, one rotation for every revolution. The balance is so precise that it has lasted for billions of years without breaking. That gravitational connection extends beyond tides. The Moon stabilizes the Earth's axial tilt, keeping it from wandering too wildly over time. Without that stabilizing effect, the planet's tilt could vary chaotically, causing extreme shifts in climate. Mars, which lacks a large moon, experiences exactly this. Its tilt wobbles dramatically, sometimes tipping the poles nearly sideways. Earth's tilt, by contrast, oscillates gently, ensuring relatively consistent seasons. The moon's steady tug keeps the climate stable enough for life to endure. It's extraordinary that something so distant can have such intimate influence. Every wave that rolls onto a shore, every tidal current that moves nutrients through the oceans, every migration guided by the lunar cycle, all of it is connected to the moon's pull. Even life's early evolution may have been shaped by it. Billions of years ago, when life was confined to shallow seas, the tides would have exposed and submerged those regions twice a day. That rhythmic flooding and drying may have driven early organisms to adapt between water and land, setting the stage for all terrestrial life that followed. The moon, in its way, helped life take its first steps out of the sea. The lunar tug doesn't only act on water. The solid Earth itself flexes slightly as the moon passes overhead. The crust rises and falls by a few inches each day, a barely perceptible motion detectable only by precise instruments. The atmosphere moves too, creating small variations in pressure and wind. The entire planet breathes in response to the moon's gravity, every layer shifting in harmony with its orbit. There's a subtle symmetry to the relationship. The same gravity that the moon exerts on Earth, the Earth exerts back on the moon. The result is not one pulling the other, but both curving together through space, orbiting a common centre that lies about 1,000 miles beneath the Earth's surface. The path they trace is smooth and constant, an endless ellipse that repeats with quiet precision. The balance between them is so stable that it has survived impacts, geological upheavals, and the slow rearrangement of continents. It will persist until the distant future, when other forces, the expanding orbit, the aging of the sun, finally change the equation. Even light from the moon is a reflection of this bond. The glow that spills across the landscape at night is sunlight bounced off a world locked in perpetual motion with our own. That gentle light, so soft and familiar, is a visible reminder of connection, energy shared across space turned into illumination. The moon's phases, too, are markers of the geometry between the two bodies. As the moon moves through its orbit, the changing angle of sunlight paints its surface in crescents and shadows. Those phases are predictable to the second, but they still carry the feeling of something ancient, something alive in its constancy. The moon's orbit isn't a perfect circle. It's slightly elliptical, bringing it closer and farther from Earth over each cycle. That small variation changes the apparent size of the moon in the sky. Sometimes it appears larger and brighter, a supermoon, rising enormous above the horizon. Other times it looks smaller, more distant. These subtle shifts remind us that even in stability there is motion, constant, quiet motion that never quite repeats exactly the same way. Over time, the lunar tug leaves traces everywhere. Sediments on the ocean floor record the rhythm of ancient tides. Fossilized coral growth rings show how many days once fit into a year. The numbers tell the story clearly. Hundreds of millions of years ago, there were more days per year because each day was shorter. The moon has been stretching time ever so slightly for billions of years. The length of a day, the pacing of life, the measure of time itself, all are linked to that slow outward drift of our nearest neighbour. Even the word month carries the moon's legacy. Early calendars were built around its cycles, the regular waxing and waning that gave humans their first reliable measure of time. The lunar rhythm guided planting, hunting, ritual and rest. Its phases became symbols of change and renewal, reminders that all things move in cycles. Before the mechanical clock or the digital watch, the moon was the timekeeper of the world. The lunar tug is not only physical but psychological. It has been a source of wonder for every generation that ever looked up at the night sky. Poets, sailors, astronomers, all have felt its pull in different ways. Its motion, so predictable and serene, provides a sense of order in a universe otherwise filled with chaos. The knowledge that its phases will return, that its orbit will continue, brings comfort. Even when clouds hide it, we know it's there, keeping time in silence. The moon, also connects Earth to the larger mechanics of the solar system. Its orbit reflects not only the pull of our planet but the subtle influence of the Sun. The combined gravitational forces of Earth, Moon and Sun produce spring tides when the three align, and neap tides when they form a right angle. These cycles create a secondary rhythm in the oceans, adding layers of complexity to the planet's motion. It's a reminder that nothing moves alone. Every object in space, no matter how small, feels the influence of everything else. The Earth and Moon together form a double system, bound by mutual gravity and shaped by shared motion. If you could shrink the universe down to a scale small enough to hold the pair in your hand, you'd see the symmetry clearly. Two spheres circling a common point, forever exchanging energy, forever in balance. The line between them is invisible, but everything we know depends on it. Without the Moon's steadying hand, Earth's rotation might wander unpredictably, its climate veering from one extreme to another. The calm regularity that allows life to thrive owes its existence to that faint, constant tug. From our perspective, the Moon seems to glide effortlessly through the sky. It rises, crosses, and sets in silent grace. But beneath that serenity lies a slow transfer of momentum, a balancing of forces that defines the evolution of both worlds. The Moon may drift farther away, but its influence will never fade completely. It has left its mark in the tides, in the rhythm of days, in the stability of seasons. It has shaped the Earth itself, turning chaos into harmony through nothing more than the steady application of gravity. When you stand beneath a full moon and feel the world washed in its pale light, you're seeing not a passive reflection, but the visible face of a dynamic bond, a relationship that has endured longer than life itself. The Moon's presence is a reminder that motion can be gentle, that influence need not be violent to be profound. Its pull has slowed the Earth, shaped its oceans, and guided its history without a single sound. And as the planet keeps turning, the Moon continues its slow, patient orbit, always slightly ahead, always slightly pulling back. Together they move through space, bound not by chance but by the inevitability of motion. The same motion that began in the first turning of the cosmic clouds. The lunar tug is the Earth's most intimate connection to the wider universe, a constant exchange between two worlds that spin together endlessly in quiet, perfect balance. When we think about spinning, we tend to picture the vast and visible, planets turning, moons orbiting, galaxies twisting through space. But motion does not begin there. It begins much smaller, in places beyond the reach of our senses. Every solid surface, every drop of water, every breath of air is made of particles, and each of those particles carries its own kind of rotation. The universe's dance does not end at the cosmic scale. It continues deep within the structure of matter itself, in the secret spins that make everything what it is. Inside everything around you, the chair you sit on, the air that fills your lungs, the atoms that build your body, there are particles moving in constant, quiet motion. They are not simply sitting still, waiting to be noticed. They vibrate, they orbit, they turn, and even those that seem to be standing still possess something intrinsic, something built into their very nature: spin. At the level of quantum physics, spin is not exactly rotation in the way we understand it. An electron does not spin like a planet, with mass turning around an axis in space. It has no measurable surface, no internal gears to move. Instead, spin is a fundamental property, a form of angular momentum that exists even in a point-like particle. It describes not a literal twirling motion, but a kind of built-in orientation, a way the particle interacts with the universe. Spin is the quiet rhythm at the heart of matter, unseen, constant, indispensable. If you imagine an electron, it might be tempting to picture it as a tiny sphere whirling in place. That image is useful but incomplete. In reality, spin comes from the mathematics of symmetry. The equations that describe the quantum world, the same equations that govern the behavior of atoms and light, include a kind of rotational symmetry that demands that particles have intrinsic angular momentum. It's as though, in the very act of existing, every particle carries with it the memory of motion. Electrons, protons, neutrons all have spin. So do photons, the particles of light. So do quarks, the building blocks of protons and neutrons. The amount of spin each particle possesses is quantized, meaning it comes in fixed amounts. Electrons, protons, and neutrons each have a spin of 1/2, while photons have a spin of 1. These numbers define how the particles behave, how they combine, how they form the world we know. The difference between half-integer spins and whole spins turns out to be one of the most fundamental divisions in physics. Particles with half-integer spins, called fermions, make up matter. They obey the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state at the same time. This rule gives matter its solidity. It's the reason your hand cannot pass through a table, the reason atoms stack into structures instead of collapsing into a single point. The spin of fermions, their invisible angular momentum, is what makes the material world tangible. Particles with whole number spins, called bosons, behave differently. They do not obey the exclusion principle. Instead, they can occupy the same state, overlapping and amplifying one another. Bosons are the carriers of forces, photons for electromagnetism, gluons for the strong nuclear force, W and Z bosons for the weak force, and, in theory, gravitons for gravity. They are the messengers that make interactions possible. Their spins give the universe its structure of communication, the way matter feels forces, exchanges energy, and stays connected. All of this, the division between matter and force, the stability of atoms, the cohesion of light, depends on spin. Without it, the universe would collapse into uniformity. There would be no distinction between one particle and another, no shape, no interaction, no life. The secret spins within everything are what prevent everything from becoming the same. If you look closer still, the importance of spin deepens. Inside every atom, electrons occupy regions called orbitals, regions where they are most likely to be found. These orbitals are arranged according to the electron's energy and spin. The way spins align or oppose each other determines the chemical behavior of an element, how it bonds, how it reacts, how it builds molecules. The entire periodic table is a manifestation of spin rules. The structure of matter, from hydrogen to uranium, from water to DNA, is shaped by how tiny spins align. In a simple atom like hydrogen, the proton in the nucleus and the electron that surrounds it each have a spin of 1/2. These spins can align or oppose. When they align, the atom has slightly more energy. When they oppose, it has slightly less. This difference is so subtle that it's invisible to the eye, but it can be detected through radio waves. The famous 21 centimeter line used by astronomers to map hydrogen throughout the galaxy is a result of this spin interaction. The moment when the spins of the proton and electron flip from aligned to opposed, releasing a photon in the process. The very map of the universe's structure, traced by radio telescopes, is drawn in the language of atomic spin. In more complex atoms, spin interactions determine magnetic properties. When many electrons align their spins in the same direction, their magnetic moments combine, creating a macroscopic field. That's what happens in materials like iron, where the aligned spins produce magnetism strong enough to move a compass needle or lift a nail. Even in less obvious substances, spin alignment plays a role in how atoms bond and how energy moves through matter. Magnetism, electricity, chemistry, all are built from this invisible, quantized rotation. Spin also determines how particles behave in extreme conditions. In stars, where heat and pressure crush atoms together, the spins of particles dictate how nuclear fusion proceeds. When two protons fuse in the sun, Their spins must align in just the right way for the reaction to occur. Those reactions release the light and warmth that reach Earth. Every sunrise is a product of nuclear spin. Even the behavior of light itself is tied to spin. Photons have a spin of 1, but because they travel at the speed of light, their spin manifests as polarization, the orientation of their oscillating electric and magnetic fields. When sunlight passes through a filter, polarization determines what gets through and what doesn't. The color of the sky, the shimmer on water, the reflection in glass, all depend on how the spins of photons interact with matter. The play of light we see every day is, in essence, the visible consequence of quantum rotation. Spin reaches even deeper into the fabric of reality. In quantum mechanics, it creates one of the most mysterious phenomena of all: entanglement. When two particles interact, their spins can become linked, so that the state of one immediately affects the state of the other, no matter how far apart they move. Measure the spin of one, and you instantly know the spin of the other. This correlation, confirmed in countless experiments, defies classical intuition. It suggests that spin is not just a property of individual particles, but a thread of connection woven through space itself. Physicists describe spin using mathematical objects called spinors, entities that change in strange ways when rotated. Rotate a spinor by 360 degrees, a full circle, and it does not return to its original state. Only after a 720-degree rotation does it come back to itself. This odd behavior has no counterpart in the macroscopic world. It's a reminder that spin, at its core, belongs to a level of reality that behaves differently from the one we experience. It's not a mechanical twirl, but a fundamental symmetry, an aspect of how space, time, and matter interact at their most basic level. In the quantum world, motion and identity are inseparable. Spin defines what kind of particle something is. Change the spin, and you change its nature. It's not just an attribute, it's an essence. That's why physicists sometimes speak of spin as a kind of fingerprint of the universe. Every particle type is distinguished not only by its mass and charge, but by how it spins, how it turns through the geometry of space-time. And spin isn't limited to particles of matter or light. Even the vacuum of space, what we think of as empty, is filled with virtual particles that flicker in and out of existence, carrying spin as they do. These ephemeral particles give rise to measurable effects, like the tiny magnetic moments of electrons, or the forces between uncharged objects known as the Casimir effect. The quantum vacuum is not still. It seethes with motion, every flicker an expression of angular momentum on the smallest possible scale. On a larger scale, the cumulative effects of spin give rise to phenomena like superconductivity and superfluidity, states of matter where particles move in perfect synchrony. In a superconductor, electrons pair up in such a way that their spins align into a shared, stable configuration, allowing them to flow without resistance. In a superfluid, atoms move collectively, their spins linked in a single unified motion that can climb walls and flow endlessly without friction. These macroscopic quantum states are glimpses of what happens when spin stops being random and becomes cooperative. The result is motion so smooth it defies ordinary experience. Even within living systems, spin has a role to play. Recent research suggests that some biological processes, such as the magnetic navigation of migratory birds or the efficiency of photosynthesis, may rely on quantum spin effects. In the cells of certain animals, pairs of electrons react in ways sensitive to Earth's magnetic field, guiding migration. In plants, the transfer of energy during photosynthesis may involve spin-dependent quantum coherence, helping light energy flow efficiently through complex molecules. The same quantum spins that define the cosmos also guide the processes of life. The magnetic resonance imaging used in medicine works on the same principle. It detects the spins of atomic nuclei in the body. When placed in a magnetic field, those spins align slightly. Radio waves then flip them, and as they return to alignment they emit signals that can be measured. The resulting images reveal the structure of tissues without cutting or damaging them. Every MRI scan is a direct reading of the invisible spins that fill you, a map of motion turned into light. Spin also gives rise to quantum technologies, from magnetic storage in computers to the developing field of quantum computing. In quantum bits, or qubits, information is stored in the spin state of particles. Because those states can exist in superpositions, both up and down at once, quantum computers can process vast numbers of possibilities simultaneously. The entire future of computation may rest on humanity's growing ability to control and measure the spins within matter. It's remarkable to realize that the same principle that keeps planets rotating also governs the structure of atoms and the operation of modern machines. The scales differ by unimaginable amounts, but the rule is the same. Motion, once begun, persists. Angular momentum is conserved. From the cosmic to the quantum, the pattern repeats. The universe doesn't change its logic just because we look closer. And at the smaller scales, the logic is astonishingly consistent. Every spin, every alignment, every flip and reversal happens according to precise probabilities. Quantum mechanics does not tell us exactly when or how an individual spin will change, only the chances. Yet out of that uncertainty arises the solid predictability of the macroscopic world. The laws that govern spinning electrons are the same that define the rotation of stars. The difference is only in size, never in principle. If you could somehow see the secret spins within you, the electrons in atoms, the protons in nuclei, the interactions of magnetic fields, you would see a world in motion, constant and vibrant. You would see currents of angular momentum weaving through matter, linking every atom to the next. There would be no stillness, no pause, only the seamless continuity of turning. The solidity you feel when you touch something would dissolve into motion. Endless, microscopic, perfectly ordered motion. The quiet truth is that there is no true boundary between the spinning of galaxies and the spin of particles. Both are expressions of the same principle, scaled across the unimaginable range of existence. The rotation of a star and the rotation of an electron are two versions of the same language, the language of motion written into reality itself. The universe doesn't merely contain spin, it is made of it. The secret spins within everything are the threads that tie the cosmos together. They keep the stars shining, the matter stable, the life functioning. They are the invisible heartbeat of the physical world, and though we can't feel them or see them directly, they are always there, in every atom, every ray of light, every breath we take. The world turns because they turn. Deep in the heart of galaxies, where light fades and matter collapses beyond recognition, there exist objects so extreme that even the universe itself seems to hold its breath around them. They are not stars, not planets, not even solid bodies in any familiar sense. They are regions of space where gravity has become absolute, where the pull inward has grown stronger than anything that can resist it. These are black holes, the fastest dancers in the cosmic waltz, the ultimate expression of spin and motion. Everything we've spoken of, the turning of planets, the orbit of moons, the spin of stars, reaches its final crescendo in these objects. For black holes are not merely points of collapse. They are engines of rotation so powerful that they drag the very fabric of space-time into motion. If you could watch one from afar, you wouldn't see a thing fall into stillness. You'd see motion itself taken to its limit, curved into the shape of a whirlpool, twisting light and time around its axis. Black holes form from the deaths of massive stars. When a star many times the mass of our sun burns through its fuel, it loses the internal pressure that once balanced its gravity. The core collapses inward, compressing in seconds what once spanned millions of kilometers. The outer layers explode outward in a supernova, but the core keeps falling, crushed beyond the point where even atomic forces can hold it up. What remains is a singularity, a region where matter and energy are squeezed into infinite density, surrounded by an event horizon from which nothing can escape. Yet not all black holes are the same. Some barely spin at all. Others rotate at extraordinary speeds, near the ultimate limit allowed by physics. When a black hole spins, it doesn't rotate like a planet or a sphere. There's no surface turning through space. Instead, the rotation describes the motion of space-time itself. Around a rotating black hole, space and time are twisted together, forming a region known as the ergosphere. Within it, every object, every photon, every particle is forced to move in the direction of the black hole's spin. There is no choice. Even light cannot remain still. This phenomenon, called frame dragging, is one of the most remarkable consequences of Einstein's theory of general relativity. It means that massive rotating objects pull space-time along with them as they turn. The effect is small around planets and stars, but near a black hole it dominates everything. The faster the rotation, the greater the drag, until the distinction between motion and geometry begins to blur. If you could somehow stand near the edge of a spinning black hole, safely, impossibly, without being torn apart, you would feel the space around you twist. You would see light bending into spirals, the stars behind you smeared into rings by the curvature of space. Time itself would dilate, slowing as you approach the event horizon. To an outside observer, your motion would appear to freeze, your image locked at the edge forever. To you, everything would continue normally, though the outside universe would seem to race forward in a blur of ages. In that moment, rotation and time would merge into one unbroken continuum. The speed of a black hole's rotation is measured by a quantity known as its spin parameter, a value between 0 and 1. A spin of 0 means no rotation. A spin of 1 means the black hole is rotating at the theoretical maximum, the speed at which the event horizon itself would move at the speed of light. Observations suggest that many black holes approach this limit. Some, formed by the collapse of massive stars or the merging of smaller black holes, spin so fast that the space around them resembles a vortex of pure energy. At the centers of galaxies, supermassive black holes contain millions or even billions of solar masses. These titans often spin at near light speed, having accumulated angular momentum from everything they've devoured. Gas, stars, dust, entire star clusters. Each object that falls in transfers a bit of its motion, adding to the black hole's rotation. Over eons, this process turns them into the fastest dancers in the cosmos. Their rotations measured not in hours or days, but in fractions of time itself. Around these giants, matter forms glowing disks called accretion disks. As gas spirals inward, friction and compression heat it to millions of degrees, causing it to radiate intensely in X-rays and ultraviolet light. These disks are among the brightest objects in the universe, outshining their host galaxies. The light we see from them is not produced by the black hole itself, but by the matter caught in its gravitational grip, spinning ever faster as it falls toward the event horizon. Near the edge, particles orbit at half the speed of light, completing millions of revolutions in seconds before crossing the point of no return. The entire scene is a dance of destruction and creation, motion transformed into energy, energy into light. Some of that energy doesn't fall in at all. The rotation of the black hole can actually power enormous jets that shoot out from its poles, streams of particles moving at nearly the speed of light across millions of light years. The mechanism behind these jets is still not fully understood, but it seems to involve the twisting of magnetic fields in the ergosphere. The spin of the black hole transfers energy to the surrounding plasma, launching it outward in narrow beams. These jets sculpt entire galaxies, regulating star formation and spreading heavy elements across interstellar space. Even in their violence, spinning black holes bring balance to the cosmos. Rotation defines their very nature, A non-rotating black hole is described by the Schwarzschild solution to Einstein's equations, while a rotating one follows the Kerr solution. The difference between the two is not minor. The Kerr black hole possesses an ergosphere, a region outside the event horizon where energy can, in theory, be extracted. This idea, proposed by physicist Roger Penrose, led to the concept of the Penrose process. By sending an object into the ergosphere and having it split, one part falling in and the other escaping, you could gain energy from the black hole's rotation. It's a thought experiment more than a practical plan, but it reveals a profound truth. Even the most extreme darkness in the universe is not motionless. It turns, it gives, it participates in the same conservation of angular momentum that governs everything else. That connection extends further than physics alone. In a way, the black hole's spin represents the culmination of the universe's tendency toward motion. From the first clouds of gas to the turning of stars, from the birth of galaxies to the collapse of massive suns, every layer of creation passes on its rotation, compressing it into smaller and smaller spaces. The black hole is the final condensation of that process. All the angular momentum of a dying star condensed into a single spinning point of infinite density. It is the endpoint of motion that never stops moving. Even time behaves differently around such an object. In a rotating black hole, the geometry of space-time becomes so warped that there are paths that loop backward in time, theoretical curves that could connect future and past. These are mathematical possibilities, not realities we can reach, but they show how rotation bends not only space but the very structure of causality. In the presence of extreme spin, the universe itself becomes fluid, capable of twisting in ways that defy intuition. Astronomers have learned to measure the spin of black holes by studying the light from their accretion disks. The inner edge of the disk depends on the rotation rate. The faster the spin, the closer the matter can orbit before falling in. By analysing the X-rays emitted from these regions, scientists can infer how fast the black hole is turning. The results are astonishing. Some stellar mass black holes rotate at 95% of the maximum possible rate. Some supermassive ones, in distant quasars, appear to be nearly perfect spinners, their angular momentum pushing the very limits of relativity. And yet, despite their power, black holes are not eternal. Over unimaginably long time scales, they slowly lose energy through a process called Hawking radiation, a faint emission predicted by quantum theory. The radiation is negligible for massive black holes, but it carries information about their spin. As they lose energy, their rotation slows, their event horizons shrink, and eventually, after eons upon eons, they will fade away completely. Even the fastest dancers, it seems, must eventually come to rest, but not yet, not for trillions of years. For now, the universe's great turning continues. The fastest spinning black holes teach us something profound about motion itself. They show that rotation is not a simple phenomenon confined to solid objects, but a property of space-time, woven into the geometry of existence. They remind us that angular momentum is not just a number in an equation, but a kind of cosmic inheritance, something passed from one scale to the next, conserved and transformed but never lost. The light we see from distant quasars, the flickering beacons powered by spinning black holes, billions of light years away, has been travelling since before the Earth existed. Those photons carry with them the imprint of rotation, the Doppler shifts, the relativistic beaming, the signatures of matter orbiting at nearly light speed. When they finally reach us, they tell a story of motion that began long before our world took shape. They are messages from the fastest dancers, written in the language of spin and light. Even the idea of stillness loses meaning near them. The black hole's event horizon marks not a boundary of rest, but of inevitability. Everything that crosses it continues to move inward, not because it is being forced, but because motion itself has been redefined. In that region, time and space exchange roles, falling becomes living, rotation becomes geometry. There is no pause, no halt. only continuation in a form we can't yet fully imagine. It's striking how the same principle, the conservation of angular momentum, can describe both the slow turning of the Earth and the violent whirl of a black hole. The universe is consistent in its laws regardless of scale or intensity. The same physics that governs the spin of an atom governs the spin of a galaxy. What changes is only the energy involved, the depth of the curvature, the pace of the dance. And in a way, the black hole's spin connects the beginning and end of time. The rotation that started with the asymmetries of the early universe ends here, in these compact, churning remnants of stars. Yet even they are not truly final. The energy released by their spin-shaped galaxies drives evolution, seeds new generations of stars. The cycle continues, unbroken. Motion, once begun, never dies. It only changes form. If you could look at the universe as a whole, every galaxy turning, every star orbiting, every black hole spinning at its centre, you would see a vast pattern of motion repeating at every level. Each system, large or small, carries the same imprint, a memory of the first imbalance that set everything into motion. The black holes, with their furious spins, are the most intense expression of that memory, the sharpest echo of the universe's original twist. When you think of them that way, they stop being objects of fear and become symbols of continuity. They are not voids that consume, but engines that preserve, keeping alive the angular momentum that began at the dawn of time. They are the ultimate dancers in a cosmic ballet, whirling faster than imagination, shaping the galaxies around them, and reminding us that motion, even at its most violent, is the source of order, not chaos. The fastest dancers of all are hidden, invisible, yet their influence is everywhere. They hold galaxies together, bend light, and sculpt the universe's grand architecture. Through them, we glimpse the purest form of spin, motion so complete that it alters the nature of reality itself. And as the galaxies continue their slow revolutions, each carrying its spinning heart, the same pattern extends outward and inward, unending. In the turning of a black hole, we see the turning of the universe. In the twisting of space-time, we see the reflection of every smaller spin that came before. The rotation of stars, the pirouette of Earth, the spin of particles. It's all one motion, unfolding at different scales, echoing the same principle that binds everything together. The black hole, far from being an end, is the purest expression of that continuity. The universe remembering in the most extreme way possible how to turn. When you look up at the night sky and see that faint milky band stretching from horizon to horizon, you're looking along the plane of our galaxy. It's easy to think of it as fixed, a quiet tapestry of stars suspended above the Earth. But it isn't still. The Milky Way is turning slowly, steadily, carrying us with it. The light we see, the soft glow of countless suns, is part of an immense rotation, a movement so vast and so gentle that it can only be understood through patience and perspective. The galaxy is a wheel of 100 billion stars, and every one of them, including our own sun, is taking part in the same quiet revolution. Our galaxy is a disk about 100,000 light-years across and roughly 1,000 light-years thick. It's shaped like a spiral, its arms curling outward from a dense central bulge where stars cluster in enormous numbers. At its core lies something extraordinary, a supermassive black hole known as Sagittarius A, about 4 million times the mass of the Sun. Around this centre, the entire galaxy turns, a slow and majestic spin that takes hundreds of millions of years to complete a single rotation. The Sun, and everything that orbits it, is about 27,000 light-years from the centre. At that distance, we move at nearly 500,000 miles per hour. Yet, because of the immense scale, the motion is imperceptible. It takes the solar system roughly 230 million years to make one full circuit around the galactic core. When you think about it that way, the Earth has completed only about 20 such orbits since it formed. Every living thing that has ever existed, every civilization, every generation, has lived and died in a tiny fraction of a single galactic year. The rotation of the Milky Way was not always known. For most of human history, the stars appeared fixed, their arrangement unchanging. It wasn't until the 20th century that astronomers began to realize that we are inside a rotating structure. By measuring the Doppler shifts of light from different parts of the sky, they found that stars on one side of the galaxy move toward us, while those on the other move away. The pattern revealed rotation, a vast, graceful turn of the entire galactic disk. What drives this motion is gravity, as always. Every star, planet, and cloud of gas in the galaxy is bound to every other by the combined pull of their masses. But here, gravity acts not in isolation, but as part of a collective. The galaxy's mass isn't concentrated at its center, it's spread throughout the disk. That distribution means the rotation behaves differently from what we might expect. In a system governed only by visible matter, stars farther from the center should orbit more slowly, just as planets far from the sun take longer to complete their years. But when astronomers measured the speeds of stars in the outer regions, they found something strange. The stars there were moving just as fast as those closer in. This discovery was one of the first hints of dark matter, the invisible substance that makes up most of the galaxy's mass. Though we cannot see it, dark matter exerts gravitational influence, holding the outer regions of the Milky Way together and maintaining the nearly constant rotation speed across its disk. Without it, the galaxy would tear itself apart. Its stars would drift away into the dark. The slow, even turn we observe is possible only because of this hidden mass. Our sun's orbit around the galactic center is not a perfect circle. It wobbles slightly, bobbing up and down through the disk, sometimes above the plane, sometimes below. These oscillations occur over tens of millions of years, and they affect more than just the path of the solar system. As we move through regions of higher or lower density, the gravitational tides can disturb comets in the distant Oort cloud, occasionally sending some inward toward the planets. It's a reminder that the galaxy's slow turn shapes not only the motion of stars but also the events that unfold in the small spaces between them. The spiral structure of the Milky Way is another expression of motion. The arms are not solid structures but patterns, waves of density that move through the disk, compressing gas and dust as they go. As a spiral density wave passes through a region, it triggers star formation. Clouds of hydrogen collapse under their own gravity, forming clusters of newborn stars that light up the arm like scattered lanterns. Once the wave passes, the stars remain, drifting ahead while new ones form behind. The spiral arms are, in a sense, moving shadows of creation, the galaxy's heartbeat made visible. From within, the motion is almost impossible to perceive. We are inside the wheel, turning with it, and so everything seems to move together. But when astronomers map the motions of stars using precise instruments, the rotation becomes clear. The stars near the center orbit faster, those near the edges a little slower. The pattern, when plotted, forms what's called the galactic rotation curve, a smooth rise and then a plateau that extends far beyond where visible light fades. That plateau is where dark matter reveals its hand, ensuring that even the most distant stars continue their journey around the unseen center. If you could step outside the galaxy and look back, you'd see a disk glowing with billions of suns, spinning slowly against the dark. The arms would wind like soft ribbons, pale blue where new stars burn hot, and gold where older ones glow faintly. Dust lanes would thread through the light, and at the center, a brilliant mass of stars would swirl around the black hole. You'd see the whole structure rotating with silent grace, the motion so vast that even over centuries it would seem frozen, though in reality every star is rushing along its own orbit, held in balance by the gravity of all the others. The black hole at the center, Sagittarius A, anchors this motion. Its gravity dominates the innermost region of the galaxy, where stars move at thousands of miles per second, tracing tight loops that reveal its presence. Yet beyond that central cluster, the black hole's direct influence fades, replaced by the collective pull of billions of other stars and the vast halo of dark matter. The Milky Way turns not because of any single object, but because of the combined weight of all that it contains, visible and invisible alike. Even the black hole itself spins as all massive bodies do. Its rotation, though invisible, shapes the surrounding space. It can drag magnetic fields into twisted structures, power outbursts of radiation, and even help launch jets of energy from the galaxy's core. Through that spin, the centre communicates with the rest of the system, maintaining a subtle equilibrium that has lasted for billions of years. Our position in the galaxy places us in one of the quieter neighbourhoods, between two of the main spiral arms. Here, star formation is less intense, and the skies are relatively calm. It's a fortunate location. Too close to the centre and radiation and gravitational disturbances would make life difficult. Too far out and the density of material needed to form planets would drop away. The solar system occupies a kind of sweet spot, stable, protected, and gently carried along in the galaxy's slow turn. That motion shapes more than our physical environment. It defines our place in cosmic time. Every orbit the Sun completes marks a vast era of evolution. When it last returned to this point in its galactic journey, the first mammals were just emerging on Earth. When it completes the next, continents will have shifted again, climates will have changed, and whatever life exists will look upon a different sky. The galactic year is a measure of deep time, a rhythm too long for any civilization to fully experience, but one that continues regardless. The Milky Way's rotation also connects us to the greater structures beyond. Our galaxy is part of a cluster of dozens of others, known as the Local Group, which itself drifts through space as part of a larger supercluster called Laniakea. All of these structures are in motion, drawn by gravity toward denser regions, expanding with the universe even as they orbit within it. The rotation of the Milky Way is one small part of a larger cosmic flow, a local current in an infinite ocean. It's strange to think that something as immense as a galaxy could be so tranquil. From our limited view, it seems eternal and serene, but motion pervades every part of it. Stars are born and die, clouds of gas expand and contract, spiral arms shift. The entire structure flexes like a living organism, sustained by the balance between gravity and angular momentum. The slow turn of the Milky Way is not static. It is the result of countless interactions, each governed by the same laws that keep the Earth spinning and the Moon in orbit. Even in its vastness, the galaxy's rotation can be traced back to the same beginnings as everything else. The slight asymmetries in the early universe that gave rise to angular momentum. Those tiny irregularities, magnified over billions of years, became the motion we see now. The Milky Way's slow turn is, in that sense, a continuation of the universe's first spin, stretched across 100,000 light-years. Every orbit, every swirl of dust, every movement of a star is an echo of that ancient motion. If you could wait long enough, billions upon billions of years, you would see the galaxy change. The spiral arms would drift, merge, and fade. The stars would burn out, their remnants cooling into darkness. Eventually, the Milky Way itself will collide with our nearest neighbour, the Andromeda Galaxy. The two will spiral together, their stars passing through each other without direct collision, but their mutual gravity tearing apart their shapes. The merger will create a new, larger galaxy, a slow, luminous whirl that will carry on the same rotation in a different form. The Milky Way's slow turn will continue, transformed but unbroken. Even now, that future is unfolding. Andromeda is approaching at 100 kilometers per second, visible in the night sky as a faint misty patch. The collision is still billions of years away, but the gravitational attraction between the two galaxies has already begun to shape their paths. In time, The delicate spirals of both will stretch and twist, the stars weaving into long tidal streams. It will be a cosmic dance, the slow blending of two vast systems, each with its own history of motion, each contributing its spin to the whole. All of this happens so gradually that from any human perspective it feels like eternity. But the pattern is there, constant, reliable, enduring. The galaxy turns, the stars move, the sun carries us along its orbit, and we, unaware, participate in that motion. Every day, every night, we're travelling through space, not just around the Earth or the Sun, but around the centre of the Milky Way, tracing a path that has been written since before life began. The slow turn of the galaxy reminds us that motion is not always fast or violent. It can be vast, gentle, and continuous. It can unfold over timescales so long that no single being can witness it complete, yet its effects shape everything. The Milky Way's rotation sets the stage for star formation, for planetary systems, for the conditions that allow consciousness to arise and wonder about the sky. If you stand outside on a clear night, far from city lights, and look up at the glowing arc of the Milky Way, you're looking along the edge of that motion, the flat plane of the disk, where countless stars are moving together through time. You can't see the rotation directly, but it's there, written into every point of light, every faint cloud of dust. The sky you see is not a static picture. It's a living current, flowing through space with infinite patience. The galaxy turns, slowly, gracefully, endlessly. The sun turns with it. The earth turns within it. And everything you know, every atom, every breath, every moment, turns as well, caught in the same vast motion that began at the dawn of time and continues without pause, drawing all things into its quiet, eternal rhythm. From the outside, a galaxy may look solitary, a whirl of light drifting alone in the dark, but in truth, no galaxy exists in isolation. Each one is part of a greater structure, linked invisibly to others through the vast fabric of gravity. The Milky Way's slow turn is not a lonely motion. It's one step in a larger dance, a galactic ballet that spans hundreds of millions of light years, choreographed by forces that have been shaping the universe since its birth. If we could zoom out far enough, the familiar spiral of our galaxy would fade into a speck among billions. The empty space between galaxies would fill with faint filaments and clusters, forming a pattern that stretches in every direction, the cosmic web. It is the largest structure we know, and yet it isn't random. It has form and rhythm, an order emerging from gravity and motion. The galaxies are its dancers, moving along filaments of dark matter, drawn toward intersections where clusters form, swirling together in groups and superclusters. The motion is slow beyond comprehension, but it never stops. When the universe began, it was nearly uniform, a sea of matter and radiation expanding evenly in all directions, but not perfectly so. Tiny fluctuations in density, no more than 1 part in 100,000, appeared in that early plasma. Over time, gravity amplified those imperfections. Regions with slightly more mass attracted more matter, growing denser, while others thinned out. These growing concentrations became the seeds of galaxies, and the spaces between them became the great voids. The cosmic web began as the faintest imprint of quantum fluctuations, written into the early universe and stretched across billions of light years by cosmic expansion. As the first galaxies formed, they did not simply appear in place. They gathered along those invisible filaments of dark matter, moving toward the intersections where the pull was strongest. The filaments acted like cosmic rivers, channels through which galaxies flowed toward one another. Where several filaments met, clusters formed, vast cities of galaxies bound by their mutual gravity. Each cluster became a rotating system of its own, galaxies orbiting their shared centre, interacting, colliding, and merging over billions of years. The motion of these clusters is immense but measured. Each galaxy within a cluster can move at speeds of 1,000 kilometers per second, yet the distances between them are so great that collisions remain rare. When they do happen, they unfold in silence, over timescales that dwarf the lives of stars. Two galaxies approach, their outer halos of dark matter and gas mingling first. Tidal forces stretch and twist them, pulling out long streams of stars that arc across space. Then, as they pass through each other, their shapes distort, arms merging, cores glowing from bursts of new star formation triggered by the compression of gas. Eventually they settle into a single larger form, a merger born of motion. These encounters are not violent in the way we might imagine. The stars themselves rarely collide. The distances between them are too vast. Instead, gravity reshapes their collective structure, redistributing their orbits into new patterns. Over time, spiral galaxies can merge into ellipticals, rounder, smoother, filled with older stars. Each collision conserves angular momentum, transferring it from one form to another, spreading it through the new structure like a memory of the encounter. Every galaxy that exists today carries within its spin the story of the mergers and interactions that shaped it. The Milky Way is part of such a system. It belongs to the Local Group, a collection of more than 50 galaxies bound together by gravity. The largest are the Milky Way and Andromeda, each with its own family of smaller satellites, the Large and Small Magellanic Clouds, the Triangulum Galaxy, and many faint dwarfs orbiting like attendants. The entire group stretches across 10 million light-years and moves as a unit through the surrounding void, pulled by the gravity of nearby clusters. The Local Group, in turn, is part of a larger supercluster, Laniakea, a region of space more than 500 million light-years across, containing hundreds of thousands of galaxies. Within Laniakea, motion flows like a current. Galaxies drift along the gravitational contours of the cosmic web, following paths that lead toward denser regions. Our entire supercluster is being drawn toward a massive concentration of matter, called the Great Attractor, itself part of an even larger flow toward the Shapley supercluster farther beyond. On cosmic maps, these motions trace intricate patterns, lines converging like the steps of a great dance. Every galaxy's motion is part of that choreography, every orbit a continuation of the universe's unfolding rhythm. The cosmic web that connects them is invisible to the eye, but detectable through observation. By studying the distribution of galaxies across the sky, astronomers can map its filaments. The structure resembles a network of threads, glowing with clusters at the intersections. The voids between them are vast, regions where galaxies are rare, and the density of matter drops nearly to zero. Yet even these empty spaces are not truly empty. They contain thin traces of gas and dark matter, stretched into delicate tendrils that bridge the gaps. Motion persists there too, slow, smooth, guided by gravity's faint but unrelenting pull. The dark matter that forms the scaffolding of the cosmic web is what keeps this structure coherent. Ordinary matter, the atoms that make up stars, planets, and life, accounts for only a small fraction of the total mass. The rest is invisible, interacting only through gravity. Its presence is known from its effects, the way galaxies rotate, the way light bends as it passes near massive clusters, the way cosmic structures grow over time. Without dark matter, the filaments would not have formed. The galaxies would have drifted apart and the web would never have woven itself. Even so, the cosmic web is not static. As the universe expands, the distances between clusters grow and the filaments stretch. Within each cluster, though, gravity continues to bind galaxies together. The balance between cosmic expansion and gravitational attraction defines the scale of the structures we see. On the largest scales, space itself is expanding faster than gravity can overcome. On smaller scales, gravity wins, pulling matter into clusters and keeping them turning. The result is a universe that both grows and rotates, stretching outward while maintaining intricate internal motion. When we observe distant galaxies, we are looking back in time. The farther away we look, the younger the universe we see. Early galaxies were smaller, more chaotic, more prone to collisions. Their spins were less organised, their shapes irregular. Over billions of years, these galaxies merged and settled, forming the grand spirals and ellipticals we see today. The cosmic ballet is one of gradual refinement, disorder giving way to structure through the persistent action of motion and time. The same principles that govern the turning of the Milky Way govern the movements of these vast clusters. Gravity, angular momentum, and conservation dictate every step. When two clusters approach, their galaxies interact much as stars do within galaxies, orbiting around a shared centre of mass. The dark matter halos that surround them merge first, forming a larger gravitational well. The visible galaxies follow, adjusting their paths until a new equilibrium is reached. The process can take billions of years, but it always ends in balance. The dance is never abrupt. It unfolds with patience measured in ages. There's a quiet irony in how something so immense can also be so delicate. The filaments of the cosmic web are incredibly thin, a few million light-years wide compared to the hundreds of millions that separate them. Yet they contain most of the universe's mass. Within them, galaxies move like particles in a stream, their motions guided by currents invisible to the eye. The web itself is almost ethereal, but it holds the architecture of everything that exists. If you could watch the universe in time-lapse, billions of years condensed into moments, you'd see the cosmic web shimmer and shift. Filaments would grow thicker as they drew in matter. Clusters would brighten as galaxies collided and merged. Voids would expand, pushing the filaments together. The whole structure would appear alive, a vast organism breathing in cycles of creation and change. The galaxies would trace arcs and spirals, their orbits slowly adjusting to the evolving mass around them. The ballet would continue, unbroken, each movement feeding into the next. Within this grand motion, smaller dances unfold endlessly. Satellite galaxies orbit their hosts, star clusters circle their galactic centres, solar systems revolve around their stars. At every level, the same pattern repeats: rotation, balance, exchange. The cosmic web is not merely a structure but a process, the physical manifestation of motion sustained across time and space. Even light itself moves through this structure with grace. As photons travel across the universe, their paths bend around clusters, their wavelengths stretch with expansion, their energy changes with motion. The cosmic web leaves its imprint on every beam of light, distorting and guiding it, just as the dance of galaxies shapes the space between them. Every photon that reaches us carries a record of that journey, a trace of the universe's slow choreography, written in shifts of colour and time. The ballet extends beyond the visible. The distribution of dark matter determines where galaxies form. The flow of dark energy, the mysterious force driving the acceleration of cosmic expansion, influences how they move. Together, these unseen components define the rhythm of the universe's evolution. The galaxies, though luminous, are only the visible part of a much larger performance. In this context, the Milky Way's slow turn becomes a single step in a sequence too vast to comprehend. Our galaxy moves toward Andromeda, the local group drifts toward the Virgo cluster, and all of these in turn fall toward the gravitational centre of Laniakea. Beyond even that, the superclusters move with the overall expansion of space, their motion stretching toward the edge of the observable universe. It's a hierarchy of movement, each level nested within the next, each governed by the same laws. When astronomers map these flows, they find coherence where chaos might be expected. The galaxies do not move randomly. They stream along predictable paths, converging toward dense regions and diverging from voids. The result is a cosmic dance that has order but no single choreographer. direction but no destination. It's motion for its own sake, the expression of the universe's inherent tendency to balance gravity and expansion through movement. In the long future, this ballet will continue, though its tempo will change. As dark energy drives the universe's accelerated expansion, the spaces between superclusters will widen. Galaxies within each cluster will remain bound, but the distances between clusters will grow so vast that light from one may never reach another. The cosmic web will thin, its filaments stretching until they vanish into darkness. The dance will slow, but it will not end. Within each bound region, motion will persist. Galaxies orbiting, stars rotating, black holes spinning. The rhythm of rotation will survive even as the universe grows cold and sparse. It's almost comforting to know that the same physical laws that shape the swirl of a planet's atmosphere also govern the motions of galaxies billions of light years away. The scale changes, the details shift, but the underlying principle is constant. Motion organizes itself. Gravity turns randomness into form. Angular momentum transforms collapse into rotation. The universe doesn't just expand, it turns. Everywhere, at every scale, in every epoch. When you look at the faint smudge of Andromeda through a telescope, you're seeing not just another galaxy, but a partner in motion. Both the Milky Way and Andromeda are moving toward each other, drawn together by gravity, even as they travel through the larger flow of the cosmic web. Their eventual merger will be one act in a performance that began when the first atoms formed. The two will spiral together, their stars rearranging into a new shape, and that new galaxy will continue the turn, carried along by the currents that thread through the universe. The galactic ballets and the cosmic web that binds them are reminders that the universe's beauty lies not only in what is seen, but in how it moves. Everything that exists is part of this motion, the stars, the planets, the dust between them, even the space itself. The galaxies are not frozen lights, but living motions, turning in synchrony across unimaginable distances. The web that connects them is the silent music of gravity, and the dance it creates is endless. Every part of the cosmos, from the spin of an atom to the swirl of a supercluster, follows the same theme. Motion as balance, rotation as order, gravity as rhythm. The galactic ballet is not a performance we watch from outside. We are within it, moving with it, participants in the great slow turn of the universe. The light that reaches us tonight left its home galaxies millions of years ago, crossing the filaments of the cosmic web, shaped by the curvature of space and the spin of time itself. To look up is to see motion frozen into light, the quiet record of the universe remembering in every direction how to move. The universe never stops moving, even when it looks still, even when the night sky appears frozen, when the air is quiet and the horizon doesn't change. Motion continues underneath everything. It has always been this way. From the smallest quantum flicker to the turning of galaxies, the fabric of existence is never at rest. Every atom, every star, every system is caught in a dance without beginning or end. The poetry of perpetual motion is the language the universe speaks to itself, steady, precise, and infinite in variation. We live inside this motion, and yet we rarely feel it. The ground beneath us seems unmoving, though the Earth spins. The sun seems fixed, though it races through the galaxy. Even the galaxy itself drifts, carried by invisible flows within the cosmic web. Stillness, for us, is only a matter of perspective. We are part of a movement so vast and balanced that it feels like rest. To notice it requires imagination, the ability to see what never stops long enough to be seen. Motion is not an accident of physics. It is the natural consequence of the universe's birth. When the cosmos began, energy and matter burst outward, expanding and cooling. Tiny irregularities in that expansion created gravitational imbalances, and those imbalances set things spinning. Angular momentum, once created, cannot vanish. It only changes form, flowing from one system to another, scaling up or down but never ceasing. The galaxies turn because the clouds that formed them turned. The clouds turned because the early universe was never perfectly still. And the smallest particles spin because motion is built into the structure of reality itself. Perpetual motion, in its truest sense, isn't a fantasy machine that runs forever without energy loss. It's the real and profound persistence of movement that defines the cosmos. The universe doesn't stop because the laws that govern it don't allow stillness. Energy cannot be destroyed. Momentum cannot be erased. They can only change, transform, distribute themselves in new ways. The perpetual motion of the universe isn't about endless energy. It's about endless transformation. You can see this in everything that exists. A planet's orbit may last for billions of years, unbroken, stable, predictable. The same planet's rotation slows, but the energy isn't lost. It's transferred to its moon, to the tides, to heat. Stars burn through their fuel and collapse, their spin preserved in the remnants they leave behind. A neutron star, only a few kilometers across, can spin hundreds of times per second, carrying the angular momentum of a sun that once turned slowly. When that neutron star collapses further into a black hole, the rotation continues, condensed into a smaller and faster form. Nothing disappears. The energy simply changes shape. Even decay is motion. When particles transform, when atoms break apart or combine, when radiation spreads through space, all of it is movement. The heat that fills the universe, the background glow of creation, is the sum of countless motions at microscopic scales. Each vibration, each collision, each photon travelling outward contributes to the quiet hum of existence. The universe doesn't rest. It only becomes more evenly in motion, its energy diffused, its patterns stretched across greater distances. It's easy to think of motion as something separate from form, as though objects move through space that itself stays still. But that isn't true. Space and motion are one. The curvature of space-time defines movement, and movement defines curvature. Where mass exists, space bends, and that bending dictates how things move. Every orbit, every rotation, every fall is simply an object following the shape of space. What we call motion is geometry in action, the universe expressing its structure through time. The poetry of perpetual motion lies in its simplicity. The rules that create it are few, but their consequences are endless. Conservation of energy, conservation of momentum, the geometry of space-time. From these arise every swirl of gas, every orbit, every heartbeat. The laws don't change, but the patterns they produce never repeat exactly. Every system evolves according to the same principles, but the outcomes differ, creating variety out of consistency. The result is beauty, not deliberate or designed, but emergent, the natural result of motion finding balance. On the scale of life, this poetry is visible in smaller, gentler forms: the pulse of blood through veins, the movement of air through lungs, the oscillations of sound waves in the ear. Every biological rhythm mirrors a larger cosmic one. The planet spins, giving us day and night. The moon orbits, giving us tides. The earth orbits the sun, giving us seasons. Life evolved to follow those patterns, synchronizing its internal motions to the external ones. Sleep and wake, migration and growth, even the cycles of thought and emotion, all are echoes of the motions that shape the heavens. At the molecular level, motion never stops either. Inside cells, proteins fold, DNA coils and uncoils, electrons shift in chemical bonds, enzymes twist molecules into new shapes, powered by thermal vibrations that never truly cease. Even when you rest, your body is in motion. Atoms vibrate in place, molecules drift, ions flow. The sense of stillness is only the perception of balance. Motion equalized across systems, energy distributed evenly enough to feel calm. At the quantum level, stillness becomes impossible. According to the uncertainty principle, you cannot know both a particle's position and its momentum exactly. If something were truly motionless, its momentum would be perfectly defined as zero, and therefore its position would be completely uncertain. The result is that everything, even at absolute zero, retains some motion. Quantum fluctuations ripple through every field, creating a background of perpetual activity. Empty space is not empty. It seethes with the smallest possible motions, appearing and vanishing in the blink of no time at all. This quantum restlessness gives rise to effects that reach across the universe. Virtual particles appear and disappear, affecting the behavior of matter and light. The energy of the vacuum itself drives the acceleration of cosmic expansion. The universe's largest motion, the expansion of space, may be powered by the smallest motions imaginable. Perpetual motion is not a failure of stillness, but the nature of existence at every scale. When you think about motion this way, it becomes clear that time itself is inseparable from it. Without motion, time would have no meaning. A universe frozen in perfect stillness would have no change, no sequence, no cause or effect. It would exist perhaps, but it would not happen. Motion is what makes time real. Each rotation, each orbit, each vibration marks its passage. We measure time in movement, the swing of a pendulum, the oscillation of light, the turning of a planet. The poetry of perpetual motion is also the poetry of time unfolding. There's a quiet elegance in how motion weaves everything together. The same angular momentum that spins galaxies also spins electrons. The same gravitational attraction that pulls moons around planets pulls planets around stars and stars around galactic centers. The pattern is fractal, repeating at different scales, each level an echo of the one above and below. The universe, in this sense, is self-similar. Its structure emerges from motion repeated across magnitudes, like a melody played in higher and lower octaves at once. When scientists map the universe, they find that even the distribution of galaxies resembles the patterns of turbulence in fluids. The cosmic web, with its filaments and nodes, follows equations similar to those that describe the flow of water or air. The motion of matter across billions of light years echoes the motion of molecules in a stream. It's the same physics, scaled up. That consistency is not coincidence. It's the signature of a universe governed by simple rules playing out over infinite space. In that consistency lies comfort. The same motion that turns galaxies also turns the atoms in your body. The particles that make you were born in stars that spun, their fusion fires fueled by the same angular momentum that once shaped the early universe. The breath you take, the air that moves through you, the light that reaches your eyes, all are products of perpetual motion. You are not separate from the universe's dance. You are part of it, made of it, moving with it. And yet, for all its activity, the universe is calm. Its motions balance. Every force has a counterpart. The outward expansion of space meets the inward pull of gravity. The spinning of stars balances the collapse of gas. The dance of particles balances the stillness of their averages. The equilibrium isn't static, it's dynamic, maintained through continuous motion. Even chaos finds order in motion. Systems self-organize, energy distributes, patterns arise spontaneously. The poetry of perpetual motion is not noise but rhythm. Over immense spans of time, the universe's motion will change. Stars will exhaust their fuel. Galaxies will merge. Black holes will spin down. The expansion of space will stretch light into darkness. But even then, motion will persist. Particles will drift through the cold. Black holes will evaporate through quantum processes, releasing the last traces of their rotation. The universe will fade towards stillness, but perfect stillness will never come. Even in the farthest future, the faint whisper of quantum motion will remain. That persistence gives meaning to existence. Without motion, there would be no creation, no transformation, no life. Motion allows complexity to emerge, the circulation of energy, the formation of structure, the rise of consciousness. It connects every moment to the next, ensuring that nothing is ever truly isolated. When you trace the line of motion backward, you find the beginning of everything. When you follow it forward, you find the continuation of everything. There is no gap, no pause, only flow. The poetry of perpetual motion doesn't speak in words or sounds. It speaks in patterns, in orbits and oscillations, in waves and spirals, in the way light bends and particles spin. Its language is mathematical, but its effect is emotional. To see motion as universal is to see connection, to understand that nothing truly stands apart. Every movement, no matter how small, contributes to the unfolding of the whole. If you sit quietly and listen, not with your ears, but with awareness, you might sense it. The hum of blood in your body, the pulse in your wrist, the slow rhythm of your breath, the rotation of the planet carrying you through space. Each of these motions is a verse in the same cosmic poem. You don't need to move to participate. You already are motion, written into existence by the same forces that turn the galaxies. The universe doesn't need to rest. Its balance is motion. Its structure is rhythm. Its story is one of continuity. Energy flowing endlessly through different forms. Angular momentum changing hands from clouds to stars to planets to atoms. Even thought, even awareness may be a kind of motion. Electrical signals moving through the brain, patterns shifting and reforming, consciousness flowing in time. The more we learn about the universe, the more this pattern reveals itself. From the swirl of galaxies to the spin of subatomic particles, motion is the common thread. It connects the vast and the tiny, the past and the present, the physical and the conscious. It is the universe's way of remembering what it is, an endless, self-sustaining dance. And though the motion is constant, its experience is always new. The same Earth that spins today will never occupy the same place twice. The same stars that circle the galaxy will never align in quite the same way again. Every orbit, every spin, every pulse is unique. The repetition is an illusion. The motion is continuous, but the configurations it creates are always changing. That change is the essence of time, and time is the essence of being. Perpetual motion is not about speed. It's about endurance, the quiet certainty that movement will continue no matter how long we watch. It's the reason stars shine, the reason seasons turn, the reason atoms remain alive with energy. It's the heartbeat of the cosmos, steady and unfailing. And in that endless movement, there is a kind of peace. The universe doesn't hurry, it doesn't resist. It turns gracefully, endlessly, without effort. The poetry of perpetual motion is written not in urgency, but in patience. The patience of galaxies turning for billions of years, of stars pulsing in silence, of atoms spinning for eternity. It's the calmest motion imaginable, and the most complete. Somewhere, at every moment, a new star begins to turn, a planet begins to orbit, a particle flips its spin. Somewhere else, another completes its cycle and transforms. The balance remains perfect. The rhythm continues. The universe breathes in motion, and through that motion, everything endures. There is a moment just before sleep when the world feels completely still. The air softens, thoughts slow, and the body begins to surrender its weight to the quiet. Yet even then, when everything within you seems to pause, motion continues. The planet is turning beneath you. The stars are shifting above you. The very atoms in your body are vibrating with quiet energy. The stillness you feel is not the absence of motion, but your alignment with it. The perfect synchrony between your own rhythms and the rhythms of the universe. You are part of a world that never stops turning. Every moment the earth spins toward morning somewhere and toward night somewhere else. Every second, the moon circles above the oceans, drawing the tides across the surface of the sea. Every heartbeat, the planet carries you thousands of meters through space. The sun, too, is moving, orbiting the galactic center at hundreds of thousands of miles per hour. And beyond that, the galaxy itself is gliding along filaments of dark matter, joining a flow that stretches beyond sight. Everything, everywhere, is in motion. And you, resting in your own quiet space, are woven into that motion completely. It's strange to think that rest and movement can exist together. We tend to imagine them as opposites, one still, the other active. But in truth, the deepest rest comes not from stopping, but from moving with the world instead of against it. The universe doesn't pause, it continues, smoothly and endlessly, and peace lies in remembering that we move with it. To rest is not to resist motion, but to let it carry you, to let the spinning Earth, the orbiting moon, the travelling sun, and the turning galaxy all hold you within their rhythm. If you could step outside of everything for a moment and watch, you would see yourself drifting through an infinite choreography of motion. The planet would spin beneath a blue-white sun. The sun would orbit within the Milky Way, which would turn slowly among billions of others. From a distance, it would look like a single pattern, every level connected, every movement a reflection of the rest. You would see that there is no such thing as stillness anywhere in existence, only balance. And within that balance, everything finds its place. The oceans rise and fall, the atmosphere flows, continents drift over geological time, mountains lift and erode, rivers carve their paths. Each movement, no matter how small or slow, contributes to the harmony of the planet's rotation. The Earth's turning brings day and night, the cooling of shadow and the warming of light, the alternation that sustains life. Every sunrise and sunset is a product of that rotation. The world quietly turning you toward the sun and then away again, in a motion so steady that it feels eternal. Even the patterns of your own body are shaped by that turning. The cycles of sleep and wakefulness follow the planet's rotation, guided by light and darkness. Inside you, countless biological clocks keep time with the Earth's spin, responding to the rhythm of its days. The heart beats, the lungs expand, neurons pulse in waves of electrical motion, all tuned to a cadence that began before life existed. The same forces that turn galaxies shape your breath. The same laws that guide planets in orbit govern the flow of blood in your veins. You're not separate from the universe's motion. You're its continuation, expressed in smaller form. Rest, then, is not an interruption of motion but an alignment with it. When you sleep, you're carried through space just as when you wake. You turn with the planet, orbit with the sun, drift with the galaxy. You move through the same space as stars, clouds of gas, particles of dust. Even in your quietest moments, you're participating in a movement so vast and gentle that it feels like calm. The universe doesn't need to stop for you to rest. You rest by being part of it. The knowledge of that can be strangely comforting. It means there is no effort required to belong. You don't have to reach out to connect to the world. You already are part of it, inseparable from its movement. You have always been in motion. From the instant the atoms that make up your body were forged in the cores of stars, to the moment those atoms found each other again to form you, to this exact second as you breathe, turning with the earth beneath the quiet of the night. Even your thoughts follow patterns of motion. Electrical impulses ripple through neural pathways, memories form and dissolve, ideas circle and return. Consciousness itself seems to flow, a continuous stream that mirrors the unbroken motion of the cosmos. The rhythm of your inner world is a reflection of the rhythm outside. Slow, complex, beautifully balanced. To rest is to let those rhythms align, to stop struggling for stillness and simply allow the motion to carry you forward. There is something deeply peaceful in understanding that nothing is ever truly lost, only transformed. The spin of the world will one day slow, the sun will eventually fade, the galaxy will change its shape, yet the motion will not end. It will simply become something new. Angular momentum will pass on, from collapsing stars to swirling nebulae, from merging galaxies to new structures yet to form. Even the farthest future, the one beyond imagining, will still contain motion at the smallest scales. The universe remembers how to move, and it never forgets. When you think of your place in this, it may seem small, but that smallness is not insignificance, it's intimacy. The same principles that turn galaxies turn you. The same forces that hold stars in orbit hold you to the Earth. The same light that travels across the universe falls gently on your skin every morning. You're made of the same matter, following the same laws, part of the same continuous unfolding. When you rest, you're resting in the same motion that moves galaxies, resting in the same rotation that shapes time. If you could feel the Earth's turn directly, if you could sense the 1,000 miles per hour of rotation beneath your feet, you might never stand still again. But you don't need to feel it to know it's happening. The evidence is everywhere, in the shifting of shadows, the direction of the wind, the slow drift of stars through the night. Every motion around you is a trace of that rotation, a reminder that the world beneath you is alive with movement. The peace comes from knowing that you don't need to hold yourself separate from it. You're already part of the turning. In the night sky, when you see the constellations rise in one direction and set in another, you're watching the rotation of the Earth expressed as light. The stars themselves are not moving that way. It is we who turn, our perspective changing as the planet spins. That gentle illusion is one of the oldest companions of human awareness. Long before people understood what caused it, they watched the sky move and found meaning in its regularity. They built calendars from it, stories from it, songs from it. The Earth's spin became the heartbeat of culture as well as of nature. That rhythm has never stopped. Every revolution of the planet brings renewal, night into day, season into season. The repetition is never exact, but it's close enough to feel eternal. The world turns, and through that turn life persists. Plants follow the sun, animals move with the tides, and people live by the patterns of light and dark. Every form of life on Earth has learned to rest and wake with the turning. You are part of that pattern, sharing the same rhythm that has guided the planet for billions of years. When you lie down and close your eyes, the motion doesn't leave you behind. It carries you gently, effortlessly through space. The bed beneath you, the walls around you, the entire world is turning with you. The stillness you feel is a shared illusion. Everything moves together so perfectly that you feel nothing at all. That is what peace truly is. Motion so balanced that it becomes indistinguishable from calm. The planet's rotation is quiet, but its consequences shape everything. It defines time, climate, even the structure of memory. It connects the physical and the temporal, reminding us that time and motion are two sides of the same process. Each day is a full rotation of the Earth, each year a full orbit around the sun. Every lifetime is a series of turns within turns, smaller cycles nested within larger ones. To live is to move through those cycles to find your rhythm within them. Even the concept of rest depends on motion. Without the alternation of light and dark, without the rhythm of day and night, there would be no signal to slow down, no cue for the body to release. Rest exists because the Earth turns, because the light changes, because the world creates pauses within its motion. The act of resting is a form of participation, an acknowledgement of the planet's rhythm. You're not stopping when you rest, you're aligning yourself with the flow that makes rest possible. As the night deepens, the stars above you seem still, but they are moving too, each one orbiting the center of its own galaxy, each galaxy part of a greater web. The light from those stars has been traveling for thousands or millions of years, crossing space that has stretched as it went. When it reaches your eyes, you're seeing a moment from long ago, a record of motion preserved in light. The universe reveals itself not through still images but through movement captured across time. You're looking at motion made visible, the slow unfolding of existence written across the sky. The light enters your eyes, becomes signals in your brain, becomes understanding. Even perception itself is motion, photons absorbed, neurons firing, thought arising. Awareness is not separate from the universe's turning, it is another way for that turning to know itself. In every sense, you're resting inside the motion of the universe. The air you breathe has circled the globe countless times. The atoms in your body have travelled through stars, through oceans, through the breath of other living things. The energy that keeps you alive was once sunlight, and that sunlight was once nuclear fire inside a turning star. Motion connects every piece of you to every piece of everything else. And so, when you rest, you are not falling out of the dance, you are falling into it. The same turning that moves the Earth through space moves you through your own cycles of waking and sleeping, thinking and dreaming. The same angular momentum that keeps planets steady keeps your heart beating in rhythm. Rest is not separate from motion, it is its gentlest form. The night sky, still and vast, is the perfect mirror of this truth. The stars do not rush, the galaxies do not hurry, yet everything moves. Time passes, and with it, every particle in the cosmos shifts. You are part of that passage, a small conscious moment in an infinite continuum of motion. The peace you feel as you drift towards sleep is not an escape from that reality, but a return to it. You are resting at last in the turning world,